Hello students, welcome to the topic 4 of JEE Mains Crash Course series. This is your friend Sumit and today we are going to discuss electrostatic, potential and capacitance. This particular topic is having decent weightage both in mains and in advanced. The capacitance topic is very important. Questions are asked from this in mains as well, in advanced as well, and electrostatic potential and I'll say potential energy. Yes, that is also important. So in this video, I'm going to cover all these concepts in great detail at the same time show you how to solve the questions. And with that, you'll get hand-picked set of questions for you from the topics which are expected in 2026 that will be given in the description box. So you'll get the notes as well and the practice sheet as well. You click the link, you'll go to the app, from there you can access that. Make sure, as you know, PW platform is one of the most trusted platform from where thousands and lakhs of students prepare for competitive exams, and so many students get very good AIRs from there. So at this platform we give high quality teaching at affordable prices, and let us begin the section. So let us begin our discussion. So we'll be covering all the details in this chapter. The major topics I'll say: the potential energy, the potential and the capacitor. Beginning with the first subtopic. Okay, first of all, let us discuss how our electrostatic force is basically conservative in nature. You know that the gravitational force is conservative in nature. How? If I ask you, you'll say, sir, the work done by that is independent of the path. Yes, and that is non-dissipative in nature. What is that? Let us take, if you throw a ball vertically upward. Now, when the ball is going vertically upward, at the maximum height it stops. Okay, so what is the work done by the gravitational force, whether that is positive or negative? You will say the force is in the downward direction, displacement is in the upward direction, the work done is negative. Where that work is? Now that work, I'll say this negative work is there. So negative work means there is decrease in the kinetic energy, and that energy is stored as the potential energy. Okay, when you release it, it will come back, gain the kinetic energy. Okay, so in conservative forces, the work done, or I'll say the negative of the work done by the conservative force, is equal to the change in the potential energy. All the central forces are conservative in nature. Electrostatic force, that is a conservative force. Okay, so it follows the same funda. What funda? That the negative of the work done by the electrostatic force negative of this work done, this is equal to my change in potential energy. Okay, it's not by external force, don't get confused. This is negative of work done by the electrostatic force. Okay, now let us take, I'm having a charge particle, there is some electric field, and that charge particle, let us take, is moved from A to B. Now I want to find how much is the change in the potential energy when it is going from A to B. So first of all, what we need to find? We need to find how much work is done by the electric field. What is work done? Formula, you know that work done is basically what? Integration of F dot dr from initial position to final position. This is how we write it. Okay, so similarly here, if I write the work done by the electrostatic force, what is the electrostatic force? Electric field into the charge q. My charge that is moving is q. Okay, so electric field into the charge, so that is E into q. Okay, this becomes my electrostatic force. This is E dot dr, and this r is going from A to B. This as it is going from A to B, so I'll say some initial position A to some final position. Now this is work done. Negative of this work done, minus, and this is equal to change in potential energy, final potential energy minus initial potential energy, UB minus UA. Okay, so this is how we relate potential energy. Now generally we talk about change in potential energy. Okay, but let us take, if I ask you what is the potential energy at a point, so how will you say that? For that we need to take a reference, because in, as you know, in work energy power chapter, when we used to consider the potential energy, we used to write mgh by taking a reference. Okay, this level I'm taking that the potential energy is 0, okay, any height above h, the potential energy become mgh. So we need to define a reference, okay, then only we can say that at a particular point the potential energy is this much. So we will come to that also. Now let us talk about the relation between potential and potential energy. So basically potential is defined as the potential energy per unit charge, okay. So as I wrote that potential energy final minus initial was minus of integration of the electrostatic force was EQ dot dr, okay, and this was from A to B. This is how this was UB minus initial was UA, okay, and let me write UA here instead of this, okay. Now if I say what is the potential difference, so we will say that potential difference will become potential energy per unit charge. So divide this with charge, divide this with charge, and this becomes the potential difference. Potential we denote with V, okay. So I'll write VB minus VA like this. Now you got the relation between the potential and the field. What is that? VB minus VA is equal to integration with a negative sign E dot dr from A to B. Okay, this is how we define the relation between the potential and the field. Now if you have to find the potential difference between the 2 points, you'll just integrate it like this. What is the unit of potential? We know that is volt, okay, and if here you see, what is this? This is energy, so energy is joules. What is this? This is charge, so per coulomb. So per coulomb, so 1 volt is basically 1 joule per coulomb. Getting it? Okay. Now electrostatic potential due to a point charge. Now we will do the same exercise. Here we need to find potential due to a charge. So I am considering, let us take a charge here Q. I need to find potential from at a point, let us take that point as here. But as till now we have understood how to find the difference of the potential. So what we can do, let us take 2 points and let us find the difference between the potential of the 2 points. I am considering 2 points here A and this point as B, and they are on the same straight line. Let us take okay, and let us take this distance as RA and the distance of B point is RB. Now if I write the formula, which formula we wrote till now? We wrote that VB minus VA is equals to minus integration of E dot dr, okay, from A to B. This is what we wrote. Now if I ask you what is the electric field due to this point Q, you will say that is KQ by R square. So E I'll write as KQ divided by R square dr. Now direction of electric field and dr vector, if you see the dot product, both the angles, if you see this and this, okay, they are along the same line. My electric field and my dr is along the same line. So if I take the dot product, it will become E dr cos 0. Cos 0 means 1. So E dr. So E is this and dr is dr, and it goes from RA to RB. Further I can write this as minus KQ, integration of 1 by R square is minus 1 by R. So minus minus will get plus 1 by R, limit from A to B, RA to RB, okay, RA to RB, and from here I can say this comes out to be KQ 1 by RB minus 1 by RA, and this is my VB minus VA. Now we are able to define the difference, but what about the potential at a point? So for that we need to take reference. So let us consider the reference at infinity. Okay, in general, whenever we talk about the potential, okay, so we consider the reference to be at infinity. So at infinity, my potential is 0. That is considered. If distance becomes infinity, the potential is 0. So let us take B as infinity. So I am considering B as infinity. So RB will become infinity. B is the point at infinity. So at infinity, the potential is 0. So this will tend to 0. So we will tend to 0 here. So this will become 0 minus VA is equals to 1 by infinity is 0. So KQ with a negative sign by RA. So at any point at a distance R, this point A, let's take it is at a distance RA, the potential is KQ by RA. So if any point is at a distance R, potential will become KQ by R. We got the formula that V is equal to KQ by R. Now this formula is very important and you need to understand it and memorize it. Potential due to a point charge at a distance R is equals to KQ by R. Potential is scalar. You know, here dot product is there. It's a dot product. So if we take dot product, what we get? A scalar quantity. So potential is not a vector, it's a scalar. And the good thing about scalar is need not worry about direction. If there are multiple point charges, if I ask you potential, just find the magnitude, add that. If charge will become negative, potential will become negative here. Okay, that positive negative sign will be there. Like if let us say Q is positive, when you will put the value, the potential will become positive. If Q is negative, it will become negative. Okay. Now K, what is this K? K we know that is 1 by 4 pi epsilon naught. Epsilon naught is permittivity of free space, and for free space, this value comes out to be this. This you are already familiar with. Now, coming to some questions on this. Let us discuss first question. A point charge of 2 into 10 to the power minus 2 coulomb is moved from P to S in a uniform electric field. The electric field is given to us. Now here uniform. Directed along positive x-axis. If coordinate of P and S are given, okay, work done by electric field will be. Now here we have to find work done by electric field. Okay. Let us write it. How we will write? Work done by electric field is basically equal to what? Minus of integration of, not minus, sorry, that is integration of the electric field. What is that? E into Q. This is the force due to electric field dot dr. This is how we will write. Now electric field is along x-axis, so when I write it here, so I'll write it like E, what is Q? Q is 2 into 10 to the power minus 2. So 2 into 10 to the power minus 2. And what is E? E is 30 I cap, okay. So this is 30 I cap dot dr, okay. Now dr I can write here separately as dx I cap, dy j cap, dz k cap. So I can write dx I cap plus dy j cap plus dz k cap. Perfect. Now if you take dot product, it will become 30 into dx just. So what it will become? 6. 3 into 2 is 6 into 10 to the power minus 2. Minus 1 it will become into 10 to the power minus 1 into dx. And x goes from, now here x is going from 1 to 0. X goes from 1 to 0. So initial limit, final limit like this. And what it will become now? This will become 0.6 into dx integration is x, 0.6 was constant, therefore I took it outside, and it is going from 1 to 0. So 0 minus 1, so a negative sign will come, so minus 0.6. And everything is in SI unit. So this point is there. Everything is an SI unit. So what it is now? So I can say this comes out to be minus 600 millijoule. Okay. Just with the clear concepts, we are able to write it like this. Now sometimes what happens, it is mentioned that a charged particle is moved very slowly by an external force. Okay. Now you write the work done by the external force. Then what to do? Now you have to understand that work done by the electrostatic force is negative of the potential energy. Work done by the electrostatic force is negative of the change in potential energy, work done by the external force will be equal to change in potential energy plus, because total work done is zero if the charge particle is moved slowly. Okay, let us take electrostatic force is doing some work. Okay, the same amount of work will be done by the person, equal and opposite, equal and opposite. So therefore, when we say work done by the external force, we say that is equal to change in the potential energy. If we say work done by the electrostatic force, we will say that is negative of the change in potential energy. So don't get confused. I am writing it again here. Where should I write? Okay. So here, let me write on the previous page here. So when I say work done by the electrostatic force, what is that? That is negative of change in potential energy. If I ask you work done by the external force, this will be what? Change in potential energy. Okay, this is for when charge particle is moved slowly. Is moved slowly. Very slowly, slowly means what? The kinetic energy will remain zero. Okay, initially it was red, I am moving it very slowly. How much work I will do? I will do the same amount of work in magnitude but in opposite sign as that of the electrostatic force. Okay. Yeah. Another question, what is that? An electric charge 10 to the power minus 6 microcoulomb is placed at origin, okay, 0, 0, of XY coordinate system. The 2 points P and Q are situated at this and this respectively. The potential difference between the points P and Q is. So now we will use the formula directly. I am not going to integrate this. I am not going to integrate here. I can use the formula directly. Which formula should I use? V is equals to KQ by R. So if I write the potential at P, that is K into Q divided by the distance from the charge. The charge is at 0. What is point P? P is root 3 comma root 3. So what is the distance of root 3 comma root 3 from origin? You will say that is root of x square. So root 3 square will become 3 plus y square. So this is root 6. Okay, this is the distance of point P, RP. So this root 6 will be put here. Now similarly, if I write VQ, again we will say that is K into Q divided by RQ. Now let us write RQ here. What RQ will be? So again I will say RQ is equals to root of, what is the points? Root 6 comma root 0. Okay, root 6 square is 6, 0 square is 0. So this comes out to be root 6. Putting it here, back, root 6. If you see, Vp is equals to Vq, because that depends on the distance. If the distance of both the points is same, we can directly see the distance of both the points is same, the potential is same, the difference between the potential has to be 0. Answer C. Okay, another question. Electric potential at a point P due to a point charge of this magnitude is 50. The distance of P from the point charges. Now if you see, you may say, sir, very simple questions. But these questions are asked. You see, this is 2023. This was in 2024. Previous to that was in 2023. So these simple questions are asked. Although it seems very simple, just apply formula KQ by R, find R, isn't it? Let us do that. So KQ by R is given as, let us take V. So if I have to find R from here, what we will say, that is KQ by V. Now put the values. What is K? K we know 9 into 10 to the power 9. By the way, it is mentioned also. 9 into 10 to the power 9 into Q. What is Q? 5 into 10 to the power minus 9. divided by V. What is V? V is 50. Putting it. So plus 9 minus 9, 5, 10. Okay. And what it becomes? 0.9. This becomes 0.9. So 0.9, what is the unit? Everything we took in SI units. So answer will also be in SI unit. So 0.9 meter. 0.9 meter means 90 centimeter. So this you have to be clear with. Like whenever, let us take, you are doing a big calculation, so many numerical values will be there. So better to be on safer side, keep everything in SI units. If you keep everything in SI units, your final answer will be in SI units. So final answer will be in SI unit. Now you see whether it is in centimeters, the option are in centimeters or meter or like that. Okay, you can convert and write it accordingly. Electrostatic potential of a discrete system of charges. Now till now we discussed potential due to 1 point charge. Okay, 1 point charge is there at a distance r. If I ask you, you'll say potential is kq by r. What if there are multiple charges? Now let us take, there are multiple charges. This is charge q1. This is charge q2. This is charge q3. Here is some charge q4. And I am asking you, what is the potential at a point P? Now what we need to do? We'll find individual potentials, then just add that. Do we need to consider the direction, take the vector resultant? No, because potential is a scalar as we discussed. Just we need to see the magnitude and add it. This distance is r1, let us take. This distance is r2. This distance is r3. Here it is r4. Now we will say that total potential V is potential due to first charge K q1 by r1 plus potential due to second charge K q2 by r2 plus the potential due to third charge K q3 by r3 plus the potential due to the fourth charge K q4 by r4, and if there are other charges also you can consider similarly. Isn't it easy? Okay, in electric field we need to consider direction and then take the vector resultant, so that is a bit, I'll say, more complicated. This is just straightforward. Now let us take an example. Considering an example that let us take, there are 4 charges q, 2q, 3q, minus q. This is a square and the side of the square is A, and you have to find the potential at the center. Let me write here with the which color? Let us take with white. So I will say find potential at V. Find potential at the center, that is V. Okay. Center of square. Now take a pause, solve it, then come back. I hope you are back. Okay. Now here just see the individual potentials. At the center I have to write. So due to this charge, how much is this distance? Total is a root 2. This is a by root 2. So due to q I'll write. So that is k q by the distance a by root 2 plus. Now due to 2q, if you write at center, that will become plus k into 2q divided by a by root 2 plus due to 3q, again I'll say that is k 3q divided by a by root 2, and then due to the last charge minus q, so considering minus, so it will become minus kq divided by a by root 2. So anyways, this is getting cancelled and this whole will become 5kq. So this is 5 root 2 kq divided by a. Getting it? So such type of questions are asked and can be asked in 2026. Potential at a point due to multiple charges. Another question. Now 4 equal charges q are placed in the xy plane. These 4 charges are there. The work done to put a fifth charge q at origin of the coordinate system is. Now we need to find work done. Okay, we are bringing, it is mentioned that the work done required to put a fifth charge q at origin. From where we are bringing that charge? We will consider by default that we are bringing that charge from infinity to that point. Now work done. Now here it is saying that work required to put. What does it mean? Work done by the external force or work done by the electrostatic force? Understood. It is talking about work done by the external force. Okay, it is work required to put, that is the external force. So if I say work done by the external force, what is that? That is the change in the potential energy. And what is change in potential energy? That is charge into change in potential. And what is change in potential? Final potential minus initial potential. Finally it is at that point. Initially it was at infinity. At infinity the potential is 0. So it is the potential at the origin. Okay, we are keeping that at origin. Okay, so V into Q. This becomes my work done. Now I need to find what is V. I need to find what is V. How to find? 4 charges are there, isn't it? 1, 2, 3, 4. Each charge is q. Okay, so if I write V, due to first charge, second charge, third charge, fourth charge, kq by r1, kq by r2, kq by r3, kq by r4. So k into q minus plus 1 by r1. What is the distance of this point? 2 from origin. So 1 by 2 plus. What is the distance of this point? That is root of 16 plus 2 square 4, that is 1 by root 20. Getting it? Of this point, it's the same 1 by root 20 plus of this point 0 minus 2, same 2. Now from here I can simplify it further. 1 by 2 will become 1 and this will become 2 by root 20, which can be written as 1 by root 5. So this is 1 plus 1 by root 5 into kq by r and into charge q. Another charge is also q. Okay, another charge is also q. So this become kq by what? That is 1 plus 1 by root 5. Okay, yeah. So 1 plus 1 by root 5. This becomes my potential. Now we will multiply that with this charge. So work done will become simply into q of that. It will become kq square and k is 1 by 4 pi epsilon naught. So q square divided by 4 pi epsilon naught and 1 plus 1 by root 5. Okay. Now in exam, if you solve this question, it will take hardly, I'll say, a few seconds. Hardly few seconds, maybe in 30 seconds or 20 seconds you can quickly solve it. 4 points are there, quickly got the potential because all the charges are equal. Another q charge is coming, multiply with that, get the answer. Now electric potential for continuous charge distribution. Till now we discussed due to point charges. 1 point charge kq by r, multiple point charge sum that all. Now if there is continuous charge summation, continuous charge distribution, that can be charge that is distributed in a wire, or it can be charge that is distributed in a surface, or a charge that is distributed in a volume. Any distribution can come, isn't it? So if some distribution is there and in that the charge is distributed in any of the configuration, maybe uniformly or non-uniformly, whatever way it is, I have to find potential at a point P. Now here what we need to do, you will say, sir, we will consider one point charge, find potential due to that, another point charge plus potential due to that, another point charge plus potential due to that, and similarly we have to cover the whole charges, whatever charges are there we have to consider all of them to find that. So it means you have to do continuous summation, means you need to integrate. Okay, what we need to integrate, we will consider a small charge here, let us take this, and this charge is dq. Due to this dq charge, I'll find what is the potential at P. Let us take this distance as R. So if I write potential at P and that is my dV, so dV is K dq by R, isn't it? I need to find the total potential, I integrate it. Okay, so integrate whole, like integrate for the whole body. So all the distances also will be there, because R is also variable, that is not constant. K is constant, you can take that out. dq is variable. Okay, so you will consider one dq, you will consider another dq, like that, and dv goes from 0 to v. Similarly from there I can say v comes out to be integration of k dq by r, or I'm using small q, so k dq by r. Now the point is, it depends how dq will come. If there is line distribution, then we need to define charge per unit length there, and then accordingly charge per unit length into my small length will become my dq. If there is surface distribution of the charge, there we need to consider small area ds, that is having charge dq. dq will have sigma charge per unit area into the area ds. If the charge is distributed in volume, let us take inside sphere, so there we will consider small volume, okay, dv, and in that dv the charge is dq. dq will become charge per unit volume rho into dv. Accordingly we will put dq there and we will integrate it. Okay, now coming to the first question, that is electric potential for uniform ring. Let us take there is a ring and we are finding potential due to the ring on its axis. Okay, this is on the axis of the ring. Same story, small charge dq there I considered. Due to this dq, let us write the potential there and let us take that as dv. So if I say dv, the potential there due to this is my k into dq divided by r. K dq divided by r. Now not that r, this is not that r, this r is the distance. What is this distance? That is this distance. How much is that? This is r, this is x, okay, so this will become root of x square plus r square, because that is the hypotenuse of this right angle triangle, okay, putting that distance here. So this will become x square plus r square root of this. This is my dv, now I need to integrate it. So from here I'll get v is equals to, k is constant, I can take that out. Now this root of x square plus r square, is this constant or variable? If I consider any charge here on the ring, the distance will be the same. So this is constant, you will take it out. So this is root of x square plus r square, and inside it will be simply integration of dq. dq integration means the total charge. Total charge, let us take that as q. Okay, so total charge is q, it goes from 0 to q. This will become k q divided by root of r square plus x square. Simple formula. Just by seeing you can write, you can like feel it. There is a point, all the distances are same, okay. So when you find the total potential, just say the total potential is kq divided by the distance, that is this, okay. Now what if I ask you, what is the potential at the center of the ring? Now at the center of the ring, this distance will remain r only, so that will become just kq by r, okay. And whichever side you go, whether you go to the right or you go to the left, the potential will decrease like in the same way. If you go at center, the potential is maximum, you are going to the right, distance is increasing, potential is decreasing, or you are coming to the left, distance is increasing, potential is decreasing. Now potential due to uniform disks, again the same exercise, like we'll consider a disk which is made up of infinite number of rings. One of the ring we'll consider, okay, due to that particular ring I'll write dV there, then I'll integrate to find the total potential due to the disk. Let us do that. Here I am considering that the charge per unit area is sigma. This is my surface charge density. Surface charge density. One of the ring I considered, here they are considering that the R naught is the radius of the disk. So at a distance R, I consider one of the ring whose thickness is dr, because the ring is there, its thickness will also be there. Okay, so its thickness is dr, its charge is dq. Due to this ring, the potential here is dV. Now what is dV? What is dV? You know the formula of potential due to the ring, that is K into the charge of the ring, that is dq in this case. Okay, so I am using capital Q, so K dq divided by the distance. Distance is this hypotenuse, root of x square plus r square. So root of x square plus r square. Point is, what is dq? Here the charge is distributed in surface. So what we will do? We'll use surface charge density. Surface charge density into the surface area, that will become my dq. Now, what is the surface charge density? That I considered sigma. So sigma into what is the surface area of this ring? What is the circumference of this ring? 2 pi r. Thickness of the ring? dr. So surface area will become 2 pi r dr. If you are not able to feel it, how I wrote, how I am saying, so what you can do is flatten this ring. It will become a strip like this. It will become a strip like this. The length of the strip is 2 pi r. The thickness of the strip is dr. So the area of the strip will, this is a rectangular strip. What is the area of the rectangle? That is length into the width. So 2 pi r into dr. Dr, putting it there, K dq divided by this. Okay, now how to integrate this? What we can do? Here you can see in the numerator we are having 2 pi r dr. In the denominator we are having root of x square plus r square. So if I consider r square plus x square as t, if I consider r square plus x square as t, you see this? R square plus x square, this is t. Now if I differentiate it, so 2r dr, x is constant, becomes my dt. So this 2r dr, this becomes my dt, and this becomes t. So it is just simple integration of dt by root t. Okay, so what is integration of 1 by root t? That will become 2 root t, isn't it? So this will become, let me write with another color. So what it will become? This is k pi sigma, okay, k pi sigma. This is dt. You see, this is dt by root of t, and this integration is 2 root t. So 2 root of t. You have to put limit also. This will become 2 k pi sigma into root of r square plus x square, okay, root of r square plus x square, and r goes from 0 to r naught. Limit is r goes from 0 to r naught. So what it will become? And 2 pi, this I can 2 pi into k. K is 1 by 4 pi epsilon naught. So this will become sigma by 2 epsilon naught. sigma by 2 epsilon naught. You see, this is k is 1 by 4 pi epsilon naught. So 1 by 4 pi epsilon naught, 2 pi is there, pi will get cancelled, 2 epsilon naught will remain. So sigma by 2 epsilon naught into root of r naught square plus x square and minus x. This becomes my final expression. Do we need to remember this expression? No, it's not required. It's not required to remember. Okay, don't memorize this. I'm just this is to understand the concept, and even if it is required, very rarely, okay, it will not be required, then you can derive quickly. Electric potential for uniformly charged shell or the conducting sphere. Now, when we say uniformly charged shell or conducting sphere means in case of conducting sphere also the charges will be on the surface of the sphere. So, it will also behave like a uniformly charged shell. So, we are having a shell. Let us take this is uniformly charged. Now, what is the potential due to this? Now, you may say whether we are asking for outside or inside, both cases, outside and inside. Okay, let us take the first case at a distance r, which is less than r, and the second case at a distance r, which is greater than r, means outside. Both we have to consider. Now, if I talk about inside, in case of conductor, inside electric field will be 0. How that is 0? We'll come to that. We'll come to that. Basic thing till now you have to understand is, okay, basically fundamental thing that you have to understand is, inside this electric field is 0 inside a conductor in electrostatic condition. Why that is? We will come to that in electrostatics of conductor. We will discuss that in detail. So, inside this the electric field is 0. It means the potential is, what is the relation of potential and the electric field? What I wrote till now, I wrote dV is equals to minus of E dot dr. It means E is basically minus dV by dr. If the not vector, this is a scalar. Okay, so this, if V is I'll say if E is 0, V is constant. Okay, from here if E is 0, V is constant, because the differentiation of a constant is 0. V has to be a constant. So, inside this I will say that V is equals to constant. Now, if V is constant, whether I write electric potential at center or I write at any point inside, it's the same. Which option is easy? So, to write at center is easy. So, if I write potential at center, any charge you consider, it is at a distance r. So, due to that charge, the potential will be k dq by r. Integrate it, because the distance due to all the charges is r only. So, it will just become kq by r. So, here V becomes kq by r. If I talk of outside, if I consider any point outside, we considered when we were writing electric field due to a sphere outside. So, there the sphere behaves like the shell behaves like a point charge that is kept at the center. Okay, so similar to here, so it will behave like a point charge that is kept at center. So, if I write electric potential at any distance, let us take r here, what will be the potential? Kq divided by this distance. Inside the potential is constant, outside the potential is not constant. Potential is maximum at surface. or means inside and surface it's the same, okay, but as we are moving away the potential is decreasing. Which relation is there? 1 by r relation is there. So if I ask you plot a curve relating the distance and the potential. Now till r is equals to r the potential is constant, okay, till here this is my r is equals to r, the potential is constant. After that the potential is decreasing, relation is 1 by r, so the curve will go like this. At infinity it will become 0 and this potential value is kq by r. This is very important. You need to learn the formula as well as the curve also. Okay, many times the graphs are given. Which of the following correctly represents the variation of potential as a function of distance from the center of uniformly charged shell? 4 options. Like the curve of electric field will also be there, so you may get confused which one is correct. So make sure inside potential is constant, will not change, outside 1 by r relation, so it will go like this. Next, electric potential for uniformly charged non-conducting sphere. If a uniformly charged non-conducting sphere is there, it means the charge will be inside the volume. Okay, charge is inside the volume. Now, in that case, what will be the relation? This is my sphere, and consider the charges are distributed like this uniformly whole throughout. Getting it? Like this. Now, if I ask you, what is the potential outside? Simple. This is a sphere. If I am talking about a potential at a point outside, it will behave like a point charge and you will say the potential is kq by r. Okay. So, the condition, what was that? R greater than r. For r greater than r means outside, if I write the potential, you'll just see kq divided by the distance r, where q is the total charge. Now the point is, what is the potential for r less than r? And here is a bit, I'll say, complex relation that comes in this particular case. Now in that particular case, let us consider I have to find potential at this point, okay, at a distance r, this point P. Now how we can approach that relation? One of the method is by using the expression of electric field. By using the expression of electric field, I can integrate to find the potential. We know that V is if I write dV, dV is basically minus E dot dr. Okay, the angle is the same, so dot dr, I can just write this as E dr. So what is E? In case of uniformly charged sphere, if you remember the relation, at a distance r, it is k q r divided by r cube. This is the relation. This is directly proportional to the distance, as we have arrived this relation in the electric charges and field chapter. Okay, you know the relation. This is k q r divided by r cube. Now k q r divided by r cube dr, and this becomes my dv. We can integrate it. Now from where to where we can integrate? The charge is distributed in this sphere. We can integrate from center to surface. Not from center to surface. We can integrate from this distance r to the surface, because we need to find at this distance r. So we will integrate from this distance r, okay, from this distance r till surface, that is my capital R, and the potential will be the potential at this distance r, okay, at r the potential I am considering is V, and at surface the potential is V surface. What is the potential at surface? R is equals to R, okay, so that will become kq by r. So potential at surface is kq by r. This is the relation. Okay. Now here how we can integrate it? Easy to integrate because nothing complicated is there. K cube by r cube is constant. We can take that out, integrate r square by 2, put the limits, and similarly also here also I can write. Okay, let us do that. It's not that much complicated now. Now if I write it, it will become K Q, the final potential minus initial V is equal to, in this expression I am taking K cube by r cube as common, that is a constant, okay, outside. So this will become minus K cube by r cube outside. Integration of r, that will become r square by 2. When you will put the limits, it will go from r to capital R like this. Okay, now you put the limits. So this will become minus K cube by r cube r square minus r square divided by 2. And this is K cube by r here minus V. From here what we need to find? We need to find V. So I will take this whole on the left and V I will take on the right. So if I simplify from here, what it will become? V is equals to, taking this to the left. If I take this to the left, this 1 by 2 expression will also be there. Okay, so this will become K cube by R with 1 by 2. So this will become 3 by 2 K cube by R. And another smaller expression will become, this is minus, minus minus plus, so it will come on the left side, it will become minus again. So minus, and that is K Q R square by 2R cube. So from here I can take K Q by 2 as common, K Q by 2 R cube as common, and this will become 3R square minus R square. And this expression we got from here. This formula is a bit difficult, seems a bit difficult, not that difficult. You need to remember it. Yes. If you are not able to remember this, at least remember or understand how it is varying. How it is varying. If you see potential at center, if I ask you potential at center, what it will be? Put R is equal to 0, this will become 3 by 2 K Q by R. That is 3 by 2 times of the surface. It means the potential at center is maximum. The potential, as we are moving to surface, the potential is decreasing, and after that when we are moving from surface to away, the potential is decreasing after that. Okay, so at center the potential is maximum, from center till surface the potential is decreasing. Okay, and that relation, that expression you may find like the relation is given, and outside this is the relation, sorry, and outside this is the relation is there. Now let us try to plot it. This is V, this is R, this is K Q by R, and this is 3 by 2. Okay, this is 3 by 2 times of K Q by R, and this is K Q by R. And here I can say, let us take, this is my R is equals to R, or till here I can take it. Now after R is equals to R, the relation is K Q by R. It will go like this simply. Okay, it will go like this, and here it will come like this. Okay, so this is how it will vary. So at least remember this, at the center the potential is 3 by 2 times and that is maximum. At the surface it is kq by r. As we move away it keep on decreasing. Try to memorize this curve at least. It may ask the relation, how the potential is varying, because these graphical relations are frequently asked. The potential due to you can say shell, the relation is there, the electric field relation, the potential relation. Similarly, due to a uniformly charged sphere, the potential and the electric field, these curves are very much asked. Now coming to the questions part, let us come to the questions. This is question asked in 2023. The electric potential at center of two concentric half ring of radius r1 and r2 having same inner charge density, that is lambda. So both are having charge density lambda. What is the potential at center? Okay. Now here if I try to write the potential, how I'll do? Due to one ring first I'll write, and due to other semicircular ring I'll write. So if due to one semicircular ring, I ask you, what is the potential at center? You will say, sir, one of the dq charge will consider. Due to that dq, the potential will be dv. dv will become k dq by r. R is constant. Anyways, any charge you will consider, due to each one the distance is the same. So if you want to write the potential, you can say just dq integration will become q. So that is just k into whatever is the charge q divided by the radius r. Now what is q there? Charge per unit length is lambda. So q will be length into charge per unit length. So q is length into charge per unit length. Okay, put it there. So this is k into q pi r lambda divided by r, and this is I can write k also, because this options are in terms of epsilon, so I can write k as 1 by 4 pi epsilon naught. So this will become lambda divided by 4 epsilon naught, independent of r. Isn't it interesting? This is independent of r. So due to first ring, lambda by 4 pi epsilon naught, due to second ring, plus lambda by 4 pi epsilon naught. So lambda by 4 not pi, 4 epsilon naught plus lambda by 4 epsilon naught. So what it is? Lambda by 2 epsilon naught simply. So two charges, two distributions were there. So you can find individual potentials, add that. Another question, here the variation, okay, like as I already mentioned, these type of questions are frequently asked. So what is asked here? A uniformly charged thin spherical shell of electric potential V radially away from the center O of the shell can be graphically represented as. Okay. Now this is a thin shell, the charge is on the surface only, the potential V inside will remain constant, outside it will be 1 by r relation. A option we got. Don't be in hurry in such questions. They seem simple but easy to be do a mistake. You can do a silly mistake. Like you may say, oh sir, I thought of electric field. Inside I thought 0. Sometimes the option is that also. Inside it is 0 and outside it is 1 by r square. Sometime it happen. Or somebody may say, sir, I thought it of electric field due to a uniformly charged, and so inside it is 1 by r relation, sorry, directly r relation, outside it is 1 by r square relation. So it seems like that. This is easy to be like it's incorrect. This is also incorrect. Okay. Another question, two thin coaxial rings, each of radius a having charges q and minus q respectively are separated by distance s. Okay. The potential difference between the centers of the rings is. So there are two rings here, and the distance between the centers of the ring, that is given to us as s. We have to find the potential difference between the centers. So let us draw the diagram first and then we will write. Let us take, this is one ring and this is another ring. the distance between the centers of the two rings that is given to us. How much is that? That is S. Yes, that is S. And the radius of the ring is A. This is A. Now, and the charge Q and minus Q. Okay. If I ask you what is the potential here, let us take this potential as V1 and let us take here this potential is V2. If I ask you what is V1, you will say V1 is K and Q by A due to this, plus we will write due to this K into minus Q divided by the distance there. Okay, so easy to write. So due to this, if I write V1, so that will become K Q by A due to this, plus due to this, so minus K Q by root of A square and plus S square. Minus Q charge is there, therefore we considered minus there. Similarly, write V2 at this point. At this point, if I write, so due to this ring, that distance will be this. So this will become K Q divided by root of A square plus S square. And then plus, not plus, minus, that charge is minus. And then minus KQ divided by the radius A. We have to find difference. Take the difference. V1 minus V2 you can do. So if you do V1 minus V2, it will become twice. It will become just twice. Okay. Yeah. So this will become KQ by A minus KQ divided by root of S square plus A square and twice of this. Option are in terms of epsilon naught. So we'll put K as 1 by 4 pi epsilon naught. Okay. So this will become 1 by 2 epsilon naught and 1 by A minus root of 1 by root of S square plus A square. B option, which option? A option is coming out to be the correct answer. Okay, now let us discuss about potential due to electric dipole. Due to electric dipole, till now we discussed about electric field. What is the formula on the axis? 2 kp by r cube. What is the formula on the I can say equatorial line? That is minus kp by r cube. These two formula you must remember, very important, frequently asked in advance also. Now discussing about potential. So potential we know, two equal and opposite charges. Let us take this is minus q and this is my q. So the potential here, if I write, and this distance let us take, that is d. Okay, so not potential, the dipole I was saying. So electric dipole here, it will become q into d. So this is my electric dipole and the direction is this. Now let us take a point somewhat here. This is point P and this is at a distance r from the center. This distance is r, and let us take this angle here as theta. Write it properly. This is r. Now if you have to write potential at P, so how will you write it? You will say there are two charges, write due to first charge and due to second charge. Add the two, that will become the total potential. Yeah, simple. Yes, this is what we have to do. So when I write due to minus q and plus q, I need to consider their corresponding distances. So their corresponding distances, that is this distance and this distance. Let us take this is r1 and this is r2. So when I say potential at P, so this will be potential due to minus q plus the potential due to plus q. What is potential due to minus q? K minus q divided by r1. This is plus k plus q divided by R2, Q I'll take common, K I'll take common. So this will become 1 by R2 minus 1 by R1. Simple. As simple as that. Yeah, everything perfect. Now the thing is, I need to find the difference between these two lengths, R1 and R2. One thing that you need to understand here is, or generally we consider is, that this R distance is greater than the distance between the two charges of the dipole, or I'll say the dipole length. Okay, so if these distances are, I'll say if this R distance is greater, we need to find the difference between the two lengths. So what I'll do, I'll make a perpendicular, I'll make a perpendicular from here to here, okay, and this will become my path difference, the difference between R1 and R2. These lengths are almost similar, almost, considering R is greater than R. So I'll make a perpendicular here. This length and this length is same, so only the difference is due to this. And what is this? This angle is theta. This is also theta only, because d is very small. So this will become d cos theta. The difference I got, but this is 1 by difference. So I'll write it as kq R1 minus R2 divided by R1 R2. So this will become kq d cos theta divided by R1 R2. Now R1 and R2, when I'm taking a product of the two distances, they are nearly similar, okay, and that is equal to R. So I'll put here R square. So this is nearly equal to R square, considering this assumption only I can say. So this will become k q d cos theta by R square. Okay, so this becomes my potential due to dipole. Now another format of this can be in terms of the dipole moment. Now we need to write actually in that term only. So q into d is p, so you can write this as k p cos theta by R square. This is one format. Now another format can be, you can write this as in vector form. I'll multiply with R and divide with R. So what it will become? P R cos theta, P dot R. So this is K P dot R by R cube. You need to remember this formula. Very important. Many times it is asked, what is the potential on the axial line? If you to consider a point on the axial line, the theta will become 90, P dot R will become 0. So any point on the, not axial, sorry, equatorial, okay. So any point on the equatorial line, the potential will be 0. Now on the axial line, if you take a point to the right, so the potential will be positive, and that will be Kp by R square. If you take a point on the left, here on the left side, that will become minus Kp by R square, because their angle become 180, P dot R. So PR cos 180, that will give us a minus sign there. So this formula is important. Let us do some questions. A point dipole P, that is minus P naught x cap, is capped at origin. The potential and electric field due to dipole on y-axis. Now this dipole is along x-axis but in the negative x direction. So this dipole is like this. Now if you ask me the potential on y-axis means this axial line. Potential on axial line is 0, as I discussed now. If you take any point on the axial line, you write potential V is equals to K P dot R by R cube. The P is like this, R is like this, they are at a 90-degree angle. So P dot R will become 0. So potential is 0. Now field, we know on the axial line, this is not axial, equatorial line. On the equatorial line, the potential is minus Kp, the field is minus Kp by r cube. So if it is in this direction, field will be in this direction, and that is minus Kp by r cube. Okay, and our options are in terms of P only. If it will be asking about the magnitude, then we'll be just writing the magnitude also, but here it is in the vector form. So this is K into P divided by r cube with a negative sign. Yes, this, and the potential was 0. Okay, another question. What is this? A distance, the distance between charges plus q and minus q is 2l, and uh, is 2l, and plus 2q and minus 2q is 4l. Okay, this distance is 2l. Here I write it. From here to here, this is 2l, and from here to here, this is 4l. That is given to us. The electrostatic potential at point P here at a distance r from the center. So from the center, this distance is r, and we have to find the potential where the value of alpha is. Okay, the potential is given, we need to find alpha. Now here this one assumption they forgot to mention, and what is that? This r is, consider this, r is greater than L. This assumption is there. Okay. Now considering that assumption, there are two dipoles. One dipole is this from minus q to q, that is towards the right. Another dipole is this from 2q to this minus 2q to plus 2q, that is towards the left. The what is the magnitude of this? So if I write due to this 2q, due to this q first, that is towards the right, and that is q into 2l. So this is q into 2l, and the other one that will become 2q into 4l, that is 8ql. So one vector is towards the right, that is 2ql, another vector is towards the left, that is 8ql. The resultant will be towards the left, that is 6ql. This becomes my P now, resultant P towards the left. Okay, this becomes my resultant dipole moment, and I have to find here at this point P. Yeah, and that is at a distance r. This distance is r, and this angle is 60 degree. Now if I write V there, how will I write the formula? Kp dot r by r cube. So Kp is 6ql dot r, so Kp r cos theta. So r, now P is this towards the left, this is r. When you consider the theta between the two, that is this angle 120. So Kp cos 180 cos 120 divided by r cube, and this will become square. Cos 120 is minus 1 by 2, so this will become minus 3 kql divided by r square. Okay, minus 3 kql by r square. Now coming to the options, now after this we will see in which format the answer is. Ql is there, r square is there, I need to put the value of k, and that is 9 into 10 to the power 9. So this will become what? So this will become minus 27 ql by r square into 10 to the power 9 volt. So this minus alpha is minus 27, so alpha comes out to be 27. So this is how we have to do such questions. In this you have to see that it is a question of dipole. They will not say in the question it is a question of dipole. You have to yourself see that this is a question of dipole by seeing plus q minus q, plus 2q minus 2q. If you see that, you can easily understand this is a question of dipole. Yes, this assumption is also there. Okay, now what if it happens that this assumption is not given? Then how will you write the potential due to a dipole? Then you need to individually consider the exact distances from plus q and minus q to write the total potential. Don't use this approximation in that particular case. Okay, the answer will change. Answer will change actually if the approximation is not there. Okay, relation between electric field and potential. So we already derived that relation, and what was that relation? That relation was dV is equals to minus of E dot dr. This relation we already wrote. Now the thing is, there is a negative sign, and this negative sign tells us that if you move in the direction of electric field, the potential will decrease. Let us take one positively charged plate is there, one negatively charged plate is there. If you move in the direction of field is from positive to negative, you are moving away from positive. So the potential will decrease. Okay. So if we move in the direction of field, the potential will decrease. Also, if you leave a charge, we know that force is equals to EQ. If positive charge is there, it will move in the direction of electric field. If negative is there, opposite to the direction of electric field. That is clear. I am not going to discuss that. But I am telling a point. If you leave a charge in electric field, according to potential energy, in which direction he should go? He will go in a direction such that the potential energy decreases. So if the charge is positive, it will move towards the right. If the charge is negative, it will move towards the left. Okay. Yes. Also, if you ask me, can we write the relation for E using that? So you can do just the opposite. E, that is minus dV by dr. We'll come to that. We'll come to that, like how we are writing this relation. I'm just writing E here first. We'll come to this, how this relation is there, how we can find the potential, how we can find the field using the potential. So that thing will come back. One more thing. Yeah, that we already got that if a charge is there, it will move in a direction in which the potential energy decreases to become more stable. Means the system moves to stability actually. Okay, if a thing is there where the potential energy decreases, its natural tendency to move in that direction. Okay, because energy is less, stability will be more. If let us take the ball is here, I leave it, in which direction it should move? Up or down? Down. Why? If it moves down, the potential energy decreases, getting more stable. Okay, if we leave it, potential energy decreases, comes down, moves in the direction. Okay, so if any field is there, just say in which direction the potential energy is decreasing. So in that direction, the tendency will be there to move. Can move in opposite direction also when you apply external force. I am applying external force, moving it up. Yes, you can do that. Okay, equipotential surfaces. Now, as the word suggests, equi means same. Potential surfaces where the potential remains the same. So, equipotential surfaces are those surfaces whose potential remains the same. Okay. So, for these surfaces, the potential is constant. How the potential can be constant for a surface? Can be, if I consider a charge q, if I ask you draw equipotential surface, we'll say, sir, we'll consider a sphere like this. All the points, the distance is same at all the points, whether you write potential here or write potential here or you write potential here or write potential here, any point you consider, the potential is same. Anywhere on this sphere, the charge is at the center, potential is same. If I draw the field lines, field is like this. Okay, the field is like this, potential is same. If you see on this surface, this field line is making 90° on equipotential surface. Isn't that interesting? Yeah. So as we are saying that E is equals to minus dV by dr. Okay. So if my V is constant, if V is constant, then I'll say that like other way also I can write. Let us write the other way around. Okay. Let us write the other way around, like dV is equals to minus E dot dr. You'll understand in a better way from here. If dV is 0, V is constant means dV is 0. If dV is 0, it means E dot dr is 0 on that surface. On that surface. It means if you move on this surface, you'll move like this. This is my dr in that case, or my r in that case. If you move in this like this, the potential remain the same. Okay, it says that the electric field is perpendicular to the equipotential surface. Write that electric field lines perpendicular to the equipotential surface. This point is very important, that electric field lines are perpendicular to equipotential surfaces, because as I was saying, if you move in the direction of electric field lines, the potential decreases. If you move opposite to the direction of electric field lines, the potential will increase. But if the potential remains same, you have to move perpendicular to the electric field lines. It means the equipotential surfaces, the field lines has to be perpendicular to the surface. Getting it? Okay. Now drawing equipotential surface due to point charge, if I say, so you can say this is one equipotential surface. Okay, let me use another color. Here the potential is same. This is another equipotential surface, another sphere, another equipotential surface. Okay, here the potentials of these equipotential surface, as we move away or in the direction of field, the potential will keep on decreasing. Here it is 30 volt. The potential of this surface is 20 volt. The potential of this equipotential surface is 10 volt. If we move further ahead, it will keep on decreasing like that. Because in the direction of field, the potential decreases. So when the equipotential surfaces, if you take like this, away from the field, keep on taking like this, the potential will keep on decreasing. Okay, this is the equipotential surface of a dipole. And if I ask you, let us take, there is a wire or rope, okay, like this, long uniform wire, uniformly charged. What is the equipotential surface for this? Now equipotential surface means the field lines has to be perpendicular. It will become a cylindrical surface like this. If you see, the field lines are perpendicular to the surface. Okay, they are moving away, radially away from this charged wire. Okay, but perpendicular to the surface. Now coming to the concept determining E from V, as we wrote first that dV is equal to minus E dot dr. Okay, this relation we already know till now. dV is equals to minus E dot dr. Now if I ask you, can you write E? Yes, we can write that. And generally if I write E in terms of its magnitude, that is just, I'll say dV by dr. But you will say, sir, where is the direction? I cap, j cap, k cap, where are the directions? Because E is a vector. How will I write that? Okay. So we write it in terms of partial differentiation. Okay. So when we say E, that is del V by del X I cap plus del V by del Y j cap plus del V by del Z del Z k cap. You may ask, sir, what is this partial differentiation? Now, partial differentiation is nothing complicated. It's just a normal differentiation considering other variables to be constant. When you are differentiating with respect to x, consider yz as constant. When you are differentiating with respect to y, consider xz as constant. Differentiating with respect to z, consider xy as constant. Okay, this is only the meaning of partial differentiation. It's differentiation only. Okay, getting it? Considering others variable to be constant, that's all. So this is how we write that expression in terms of I cap, j cap, k cap. Normally in 1D only the field potential relations are given. Normally I'm talking about. If that is, you can just use like this, because it is talking about x axis only. So I say Ex is equal to minus del V by del X simply. Okay, coming to question. Let us read this question. Work done by electric field on moving a positive charge on an equipotential surface is always 0. Now, what is work done by electric field? That is negative of change in the potential energy. What is change in potential energy? That is charge into change in potential. What is potential on equipotential surface? Same. Potential on equipotential surface is same. So work done is 0. Other way also I can say, what is work done? E dot dr. On equipotential surface, when you are moving, E and dr are at 90 degrees. So E dot dr will be 0. So on equipotential surface, the potential energy is not changing. The work done by the electric field has to be 0. So this is true. Coming to the next. Electric lines of forces are always perpendicular to equipotential surface. Yes, the force is in the direction perpendicular to the equipotential surface. If you move along the surface, the force component is 0. Therefore, I'll say the work will come out to be 0. So R is correct and it is correct explanation. A option, it's correct explanation. Another question. Now here V is given to us. If the electric potential at any point XYZ is at meter in space is given by this, the electric field at a point this will be. Okay. How we write electric field? Again, I'll say that is del V by del R. Now it is talking about only one direction x. So I'll just say E is equals to minus del V by del X, or not even del, because that we use when other variables are there. There is only one variable, so you can use D only. So I'll say E is equals to minus dV by dx I cap simply. So minus d by dx of V. What is V? 3x square I cap. So this will become minus 6x I cap. Minus 6x I cap. Okay, now here he is asking at this particular point. Now yz is also there, but I don't need that. I just need x. X is given as 1. I'll put it 1. So this will become minus 6 I cap. What is the SI unit of electric field? You may say, sir, that is Newton per Coulomb. But we, from E is equal to d by dx, we can say that is also volt per meter. Okay, so it will become 6 volt per meter directed along negative x-axis. This you have to be clear with sign. Many times they confuse with sign in questions like that. Yeah, our option was correct. Directed along negative axis. Yeah, we have to recheck when sign is there. The electric field in the region is given by this, where E is, okay, this, the value of constants A is this and B is this. Okay, if the potential at x is equals to 1 is V1 and that at x is equals to minus 5 is V2, we need to find V1 minus V2. Now we use the relation, the relation between E and V. What is that relation? We know dV is equals to E dot dr with a negative sign. Okay, now here only x is changing. Okay, electric field is along x I cap only, so I'll say just here I'll take dx. Okay, so this will become minus e dx. This is dv integrated. X is going from -5 to 1, and dv v is going from v1 to v2. So this will become v2 minus v1 is equal to E is ax plus b, putting it here, okay. Now when you integrate it, a is constant will take out, it will become x square by 2, plus b is constant will take out, that will become x there. So it will become a by 2 into x square limit -5 to 1 plus b into x limit from -5 to 1. Okay. Negative sign is also there. We need to consider that. Now I am taking negative sign inside, and if I write it, it will become 25, 5 minus 5 square minus 1, that will be 24. Okay, considering negative sign. So this will become 25 minus 1, that is 24. So this will become 12a. And here it will become first I'll put -5 and then minus of 1. Okay, so that will become -6. Here when I'll put, first I'll put, because negative sign I am considering now, first lower limit I am putting, then upper limit. So it will become -5 minus of 1, so -6. So -6b. And this is equal to v2 minus v1. Okay. Now put the value of a and b. A is 20. So this is 20 into 12, 240. What is b? B is 10. So this will become 60. So what it is? 180. Yes, I am right. A option. Now if it would be -180, I will be rechecking, like did minus plus mistake or not, because sometimes it happens, like when you're writing the equation, some negative sign was here and you missed in the next step, and then further on you calculated the sign was opposite. It may happen. Okay. Now electrostatic potential energy. So potential energy we already discussed. The change in the potential energy we considered, that if let us take I write du, that is minus dw. What is minus dw? This is work done by the electric field. Fractional work done I am saying, okay. This is work done by electric field. So that relation, that is delta u, that is minus of integration of this E dot E into Q, okay. This is the force dot dr. So this actually becomes my work done by the electric field. Du is the fractional work of that. So don't get confused. This is just the fractional work of that. Okay, it's not that there is something wrong. When you integrate it, you will get the total work done, and this work done will become my decrease in potential energy. Now, if you talk about, coming to here only, if you talk about what is the potential energy between two charges, if let us take two charges are there, and I ask you what is the potential energy between them, then how will I write that? Okay, this is one charge q, and this is another charge small q. Now, if I ask you what is the potential energy of these charges, you may say, okay, how much work we did, or how much work the external field or the electric field is doing, and from that we can find. How? You may consider initially they were at infinite separation, slowly we are bringing them closer. Okay, one charge you can keep fixed, slowly we are bringing a small q, okay, and keeping at a distance r, and then we'll see how much is the work done by the external force, and that becomes my change in the potential energy. At infinite, the potential energy is 0. At r distance, we'll get potential energy. But we need not do that work. Why so? Because we know already the potential. What is the potential here due to this charge kq by r? We derived that expression. So kq by r is the potential into this charge q. So the potential energy will become kq q by r. Simple. Okay. So this formula you need to remember. If two charges are there, q1, q2, their separation is r. So we write the potential energy to be k q1 q2 by r. Getting it? If two charges are there, q1 q2 at a distance r, their potential energy is k q1 q2 by r. Now this is the potential energy due to the interaction of q1 and q2. It's not that this is energy of one charge, no, it's interaction energy. Okay, so it's a energy of q1 due to q2 and q2 due to q1. It's a combination, I'll say. So it's a I'll say it's a potential energy of system of q1 and q2 capped at a distance of r. This is how I'll say this. Okay, so sometime what happens, like student keep on thinking where this energy is of q1 or this energy is of q2 and the total energy will be like twice of that. No, it's not like that. It's interaction between the two. Now, what if there are multiple charges? How will I write the potential energy in that particular case? Then you need to consider the potential energy between each pair and just add. That is one way. Like if I ask you, let us take, if I ask you, there is a square. Okay. This is q, this is 2q, this is q, and let us take this is minus q. If I ask you what is the potential energy of the system, the side is A. Now here you need to consider for each pair. How many pairs are there? 1, 2, 3, 4, 5, 6. 6 pairs are there. Or you can say this is 4C2. 4 into 3 by 2, that becomes 6. Okay. So 4C2, 6 pairs are there. Each pair will have energy. This pair will have how much potential energy? K Q square by A. This is 1. I got it now. This pair will have minus K minus Q. Why so? Because Q and minus Q. Product will become minus Q square. So minus kq square by A. This pair will have minus q and 2q. So minus 2q. So minus 2k q square by A. Again, this pair it is. So that is plus 2k q square by A. Okay. Now, this pair plus k q and minus q. So minus will come. So minus q square divided by the distance is a root 2. A root 2. Then this pair. That will become 2q and this is q. So 2q square only. Okay. Okay. 2q square divided by the distance a root 2. So this whole becomes my potential energy of this configuration. Or I can say one more thing. I may not say like tell the potential energy. I'll say how much work need to be done to assemble this configuration. Okay, how much work you need to do to assemble this configuration? It's just the potential energy of that configuration. Okay, sometimes the question is asked. Okay, from infinity we are bringing 4 charges, keeping them at the corners of a square. The charges q, 2q, q and minus q. How much work we need to do? This much. How much will be the work done by the electrostatic force? Minus of this. Minus of this. And sometimes he may ask you like, this is the system now, additional charge we are bringing, keeping at the center, tell the work to be done. Then what you need to do? Then you need to find the only the additional energy. How much additional energy is coming? That is due to the charge you are adding. So you are bringing that charge, keeping at the center. How much additional energy will be there? That is the interaction energy of this particular charge due to other 4 charges. How to find that? Find the potential at center into Q, that charge. Okay, find the potential at that point into Q. That much energy is the interaction energy of that with other charges. Okay, so we are having a question here. Three charges Q plus Q minus Q are placed at the vertices of a right angle isosceles triangle as shown below. The net electrostatic energy of the configuration is 0 if the value of Q is. So find the net electrostatic energy of this configuration, make that to equal to 0. From there you will get what is the value of Q. Write the expression for this. So when I write the expression of these two charges, it will become K Q into Q divided by the distance. This is right angle isosceles triangle. I am considering this side to be A, this side to be A, this will become A root 2. Why I considered? It's not given in the question, and I know that anyways that will be finally cancelled out. Okay, A will be cancelled out. So this will become KQQ by A. This is this pair potential energy. Okay, now this pair potential energy, it will become K small q into small q, again Q square divided by the distance A. Then I got this pair potential energy. Now this pair potential energy, so this will become plus K Q Q divided by A root 2, and as it is saying, put it equal to 0, because he is saying now that this potential energy has to be 0. Now put it equal to 0. From there we need to find Q, capital Q in terms of small q. Q by A we can take common out. Okay, that will become 0 anyway. 1 Q will also we will take common out. Rest it will become Q, and it will become plus small q, capital Q plus small q, and there again here plus Q by root 2, and this is 0. So this will become Q 1 plus root 2 by root 2, and this is equal to minus Q. So from here Q comes out to be minus Q root 2 divided by root 2 plus 1. A option. Everything is fine? Yeah, everything is fine. I hope there is no mistake. Yeah. So we got A as the correct option. So this type of variation may come at any point asking what is the condition, not at point, for any configuration. Sometime it is, he may ask also like what is the condition for the potential to be a point to be 0. He may ask like what should be Q such that potential at like some other point is 0 here. So what you need to do, find potential due to all the three charges there, make that equal to 0. From there you will get Q. Okay, another question. In free space, a particle A of charge 1 microcoulomb is held fixed at point P. Another particle B of same charge and mass 4 milligram is kept at a distance of 1 mm from P. Okay, if B is released, then its velocity at distance of 9 mm from P is. Understood the question? What is he saying? Let me explain it. This particle A, it is having a charge of 1 microcoulomb. It is at a point P. Now this particle B having same charge means 1 microcoulomb only, and mass here it is mentioned as 4 milligram, is kept at a distance of 1 mm. So this distance is 1 mm. This charge is fixed P. B, if you release, in which direction it will move? It will move away. So when it reaches at a separation of 9 mm, it will come somewhat here, and this separation becomes 9 mm. Okay, now that is 9 mm. Now then its velocity will be, now what will be the velocity here? I will not write will V like this, because you will get confused whether this is velocity or potential. What is the velocity here? Okay. These type of questions can be done by conservation of mechanical energy. The initial kinetic plus potential has to be equal to final kinetic plus potential, because this is a conservative force. If only conservative forces are acting, electrostatic force is a conservative force. If only conservative forces are acting, the total mechanical energy will remain same. There is no dissipation of energy. So initial kinetic and potential here is equals to final kinetic and potential there. If I write the initial potential and kinetic, how will I write that initial kinetic is 0. Okay. K initial plus U initial is equals to K final plus U final. Now initial kinetic is 0 anyway. K final will become U initial minus U final, and this is charge into potential initial minus potential final, and this is Q into K, that another charge is also Q by initial distance 1 by R initial minus 1 by R final. Wrote it properly? Hope so. Okay. Now put the values. Put the values here to solve it. R1 and R2 is there, and we need to put the value of Q also, that is 1 microcoulomb, and K we know, that is given also, that is 9 into 10 to the power 9. That's all. So this is my kinetic energy final. So this is equals to half mv square. So I'll say that half mv square is equals to my kinetic final, that is kq square 1 by R1 minus 1 by R2. And now we need to put the values anyways. So K is 9 into 10 to the power 9. Q square, 1 square is 1. Microcoulomb is there, 10 to the power minus 6 square will be minus 12. Minus 12. These distances are in which unit? Mm. Mm is 10 to the power minus 3. So 10 to the power minus 3 will come in the numerator. It will become 10 to the power 3. Now we have, let us take, now we converted that to meters. So it will become 1 by, the distance is 1 and 9. So 1 minus 1 by 9, it will become 8 by 9. And half, what is M? 4 milligram. Milli means 10 to the power minus 3, and gram, we need to convert that gram to kg also. So this whole will become 10 to the power minus 6. If it would be my gram only, we'll be writing 4 into 10 to the power minus 3 kg. Now this is milligram, so this will become 4 into 10 to the power minus 6 kg. So into 4 into 10 to the power minus 6 into V square. 9 plus 3, 12. This 9 got cancelled. 2 into 2 here and 2 into 4 here. 10 to the power minus 6 will go, 10 to the power 6 will become, taking root from here, we will get V is equals to 2 into 10 to the power 3. 2 into 10 to the power 3. Yes. Option B is there. So here the charge particle is moving. We need to see the initial potential energy, final potential energy, initial kinetic energy and final kinetic energy. That's all. Conserve the energy. We'll get the answer. Another question. Let us read it. A system of 3 charges are placed as shown in figure. If D, capital D is greater than small d, okay, small d, the potential energy of the system is best given by. Okay. Now what it is, basically it becomes like a dipole. Now this is a dipole, this is another charge q, and we need to write the energy of this interaction, this dipole and this charge, plus the interaction of potential energy of these two charges also, because he is asking the total energy.
So plus that, and this is how we'll get answer. Now in first chapter also we did the derivation for potential energy of dipole. Again here we will do, but let me tell you the formula first here. The potential energy for dipole, that is given as U is equals to minus P dot E. This is potential energy of dipole. I will derive it. After some time I will derive it. I will show it again. We have done also. Therefore, I am using it here directly. So, when I am saying this is the interaction dipole, due to this Q, you write the electric field. What is the electric field? Here, electric field at you can say at this dipole, because this distance is very large as compared to this small d. So, electric field at this, if I write at this dipole, how much is that? That is in this direction, and that is kq divided by the distance square d square. This becomes my electric field, and that is towards the left. What is P? P is in this direction. Okay, dipole is in this direction. When you take the dot product, the angle between them is 0. Okay, so I'll say this U will become minus P is Q into D, and E is kq by d square, kq by capital D square. Okay, dot, both are in the same direction, therefore cos 0, okay, that will become 1. So this becomes the interaction energy of the dipole and these two charges, plus the interaction energy of these two charges also. What is the interaction energy of these two charges? So q into minus q, so k q1 into q2, so that is minus q square divided by the distance square, that is d square. Getting it? Now from here I can take k as common, because in the answer k is taken as common. We'll put k as 1 by 4 pi epsilon naught, and minus sign also I can take because both are negative. So minus q small q d divided by d square plus, this is what? Not plus, minus q square divided by small d square. I think option A is matching. Yes. Yes. Now, why I use dipole formula? It's not mentioned. It's not mentioned. You have to think. I got it, because here plus q is there, minus q is there. The distance between them is very small. So I can use formula of dipole. Other way also you can do. It's not that only this is the way. Other way also you can do. What you need to do? You can take like interaction potential energy of these two, of these two, of these two. Add the total. You'll get the answer. But that is way complicated. Then you need to use the assumption and all, and finally you'll get the answer. This one was a bit direct. Okay, potential energy of a dipole in external field. So we had done this, but again we are doing it. We had done in the previous chapter also this derivation. This is our electric field, uniform electric field. And let us take a dipole was there initially like this, and now it is turned by an angle like this. This angle is theta. Initially this was 90. Now how much that work will be in doing so? Slowly we are turning that. How much work we will do? That work will be stored as the potential energy. How much work? Can we relate work with torque? Yes, we know that work done is equals to integration of tau dot d theta. What is torque? Torque is P cross E. So that is PE sine theta. We have to apply the same torque, okay? Therefore, I am using the same. In opposite direction we have to apply. So P is sine theta d theta, integration. Theta goes from initially 90 degree to final angle, that is theta. And this is work done, and work done is equal to change in potential energy. So this is my final potential energy minus the initial potential energy. So this is PE, then integration of sine theta. What is that? Minus cos theta, minus I'll take out cos theta, goes from 90 to theta, cos 90 is 0. So this is minus PE cos theta, and this is U final minus U initial. Now this point you have to remember, here we have considered reference at our 90-degree angle. So potential energy at 90-degree angle, this was my initial potential energy, this we have considered as reference, that is 0. So formula for potential energy at any angle theta we got as minus P cos theta, which becomes minus P dot E. Important formula, need to remember. Self energy of spherical charged shell. This is charged shell. D also need to be there. And this is spherical charge, uniformly charged actually this is. Now what he is saying is, now self energy thing, what is self energy basically? This is a shell which is uniformly charged what is the potential energy? Now potential energy, these are so many charges, each charge will be, you can say, interacting with other charges also. So there is potential, I'll say there is a potential energy, okay, interactional potential energy of these charges, and that I am saying that as the self energy, okay, that is the self energy. So how much is the self energy here? That is the point. Okay, so how to do that, how to find that? So I can say that self energy is the total amount of work I did to make this configuration. Total amount of work I did. How much work I did? So I'll say, let us take, I'm bringing slowly this positive charge from infinity, putting it here. Then again bringing positive charge from infinity, putting it here. In each of this work, I'll keep on adding all this work. Total work we'll get to by integrating that. Okay. So at an instant, let us take here charge is Q. I'm bringing a charge dq from infinity. I'm using small q, so I'll use small q, and putting it here on this. How much work I did? So dw work will be the change in potential energy. So how much was the change in potential energy of this system? That is the potential of the surface into this charge dq. What is the potential of this surface? K into q divided by the radius r into dq. Integrate it. Charge goes from 0 to q. So this will become k q square divided by 2r. This is the work I did. So this work is stored as the potential energy of the system. So this becomes the self energy for a shell. Do I need to remember this formula? No, not for mains. Okay, I just took it so that you understand this particular concept, what basically the self energy is. Another self energy of spherical charge shell. Okay, so now here we are having a this is a shell. What was the previous one? Okay, it was the same. I think self energy of spherical charge shell. There is some mistake. Okay, we got it. Okay, this we got as u is equals to the same. It's the same thing. I'm just writing it here on this slide. So that is k q square divided by 2r. It's the same thing, nothing new. It's this only. Okay, kq square by 2r. So this slide I can delete basically. It's not required. Let us delete it. Can delete it. Okay, this one and this one also. Let us do. Delete it now. Not delete it. Okay, one deleted at least. No, got deleted. This is the next one actually. What it is now? Self energy of spherical charge, non-conducting sphere. Spherical charged non-conducting sphere. So the charge is basically in the volume. How much is the self energy? So again the same thing, I'll say how much work I did to make this configuration. Here this total charge is Q. Slowly I was bringing from infinity, putting charge on this to assemble this total charge Q uniformly distributed like this. How much work I did? So let us take at an instant instant in between the charge was Q, and I was bringing small charge dq from infinity, putting it here. This charge was Q. Now the point is, this radius is increasing because charge is in the volume. Okay, so the volume is increasing as the charge is coming. This radius is r. Now when I putting it this charge Q, this make a shell on this of thickness dr. It is distributed as a shell uniformly of a thickness dr. How much is the potential due to this on the surface? K Q by R. Okay. And how much charge I am bringing? dq. This is the work I did in this. This is my dw. But this R is variable. Okay. Now I need to convert R. Okay. Or I need to convert dq in terms of charge density and R. So the charge density I can find, let us take the charge density is rho. Volume charge density. And this you can write as my total charge Q divided by total volume, because this is uniformly distributed. So this charge dq, how much will be? This is distributed in a shell of thickness dr. How much is the volume of the shell? That is surface area of the shell, 4 pi r square into the thickness of the shell dr into rho. Okay, now putting rho from there, so this will become Q divided by 4 by 3 pi r cube into 4 pi r square dr. 4 pi. So this is 3q by r cube r square dr. This is my dq. Okay, and q again I can put as rho into the volume. So if I write q also, so rho is this. Into the volume, inside volume. So this will become q r cube divided by r cube. Putting both the things, k into q rotate into dq 3q r cube divided by r cube dr. This is my dw. Integrating it. Okay, so can we simplify it from here? Or we did any mistake anywhere? Yeah, I did a mistake. This was r square. this was r square. Okay, I think everything else is fine. So let us write it out. So this will become 3kq divided by r to the power 6 into, this is r to the power 5. Yeah, and 1r was also there. Yeah, I missed that. 1r was also there. This is r to the power 4. Okay, r to the power 4 integration will become r to the power 5 by 5. Limit will go from 0 to r. So this will become 3 by 5 kq, this was square, kq square divided by r. This is the self energy here. Okay, in case of solid sphere, the charge is distributed in the volume, this becomes the self energy. Do we need to remember this formula? Not at all for mains, not required, not needed. So why I took it? Just for conceptual clarity I took it here. It's not required for mains. Electrostatics of a conductor. Now we will discuss few of the properties of a conductor in the static situation. Static situation means the electric charges are not moving. The charges are not moving. The condition is static. The current is not flowing. Try to understand. Sometimes, like when we discuss here, that the charge can only be on the surface of a conductor, not inside. And then what happens eventually? Then student thinking, how is it possible the charge cannot be inside? Charge can be inside, but here we are talking about static condition. Therefore, we'll come to each detail. So, if I talk about, this is a conductor, any shape actually, need not be spherical, because if I draw it like this, you may think it's spherical. So any shape of a conductor is there. Inside this, the electric field will be 0. At static condition. Not that when the current is flowing through the wire, there is electric field inside the wire. At that static condition, electric field is 0. Why that? If electric field is not 0, the charges that are there, they will move. Isn't it? If the electric field is not 0, the charges are there, they will move. So at I'll say electrostatic condition, the electric field inside the conductor will be 0, doesn't matter the charges are there on the conductor or the electric field is there, external electric field is there, doesn't matter what. At static condition, inside this electric field will be 0. Next point, the field lines will be at 90 degree. If let us take, there are field lines, so the field lines will be at 90 degree. Here I wrote it like this, the field lines can be in opposite direction. Okay, if I am taking positive charge, it may be opposite also. Okay, so making it like that. Let us take, okay, so it was charged, so field is like this. Okay, so the field lines will be perpendicular. There will not be any component of the field along the surface. It means it will be a equipotential surface. Yes, because the field inside is 0, the potential of whole conductor is same. Even on the surface, the potential will remain the same. Therefore, the field lines will be at 90 degree. The field lines will be at 90 degree like this. There cannot be any component. If there is a component of electric field, then the charges on the surface will move, and that is not an electrostatic condition. Getting it? That is not an electrostatic condition. Therefore, the field lines will be always perpendicular to the surface of the conductor. Okay, so I can say this is a equipotential actually. equipotential. Getting it? Yeah. Next thing we can say property is, let us take a conductor is charged. Conductor is there and it is charged. At some place here, let us take the surface charge density is sigma. If I ask you what is the electric field very near to this surface, so for that what we will do? We will draw a Gaussian surface, cylindrical like this. Okay. Now here if I write the flux through the Gaussian surface, this Gaussian surface, how much that will be? On this lower part, inside this electric field is 0. Therefore, there is no flux on this. On the other side, here, let us take the electric field is E. The electric field will be perpendicular. So, on the curved surface, the flux will be 0. Only will be through the flat surface of the cylinder, and that flux I will say that is E into the surface area of this, that is, let us take ds. Okay. So, the flux will become EDS, and this is equal to Q enclosed by epsilon naught using Gauss law. So, if I write it further, E into ds, what is Q enclosed? Q enclosed will be sigma, the surface charge density, into the area there, because that charge is only coming inside this, that is sigma ds by epsilon naught. So, electric field is sigma by epsilon naught, and that is perpendicular to the surface. So, I am writing here n cap, means this is a vector perpendicularly away. So, the electric field is sigma by epsilon naught. This point is important to understand. Okay. Now, let us take if there is some cavity. This is let us take yellow itself. So, this is my conductor, and inside this here is a cavity. This is my cavity. Okay. So, here the conductor is there. So, this is my cavity. Now, this property is electrostatic shielding, and what is that? That even if, let us take, there is external field or some charges here, if you give some charges on this, okay, whatever be it, whatever be the condition, inside the cavity the electric field will be 0. Point is, this cavity is charge free. If this cavity is charge free, the electric field inside this will be 0. This has to be charge free. Okay. This property is electrostatic shielding. What if there is charge inside? Okay. Okay. Now, one more thing. As I was saying that inside this, the electric field is 0. Okay. Inside this electric field is 0, previously also mentioned, and different logics I give. One more logic can be, if I draw a Gaussian surface, the total flux through this Gaussian surface is whatever the total, I will say, flux through this Gaussian surface, that is 0. Total flux is 0, that is Q enclosed by epsilon naught, therefore Q enclosed has to be 0. So, inside, if a conductor is there, the charge will automatically come to the surface. Okay, it will not remain inside. It give charge, it will automatically come to the outer surface at static condition I am talking about. So, yes, and inside cavity we got, if the cavity charge free means there is no charge here inside in the free space. If there is no charge outside, whatever may be the electric field, whatever may be the charge distribution, inside the electric field will remain 0. Now, if there is charge in the cavity, let us take this sphere and another sphere itself. Okay, this is my, let us take cavity, and I give a charge q here. This is metal. Okay, so this is metal, and some charge q is given, and you may consider some charge. Let us take first, it's neutral. Okay, now if I ask you, will there be electric field inside the cavity? For sure, the electric field will be there inside the cavity. Here electric field will not be 0 because electric, but will there be electric field inside this? No. Here the electric field has to be 0 because inside metal surface in static condition field has to be 0. So this is inside metal surface, the field will be 0. Now you may say, sir, the field is 0, let us draw a Gaussian surface like this. Okay, this is my Gaussian surface. Let us do that with a different color that you are not confused. Let us make a Gaussian surface, yeah, like this, but the charge is inside. If the charge is inside, some field lines should come out, isn't it? No. So what will happen? Some redistribution will happen. The sphere was neutral, so negative q charge will come. Okay, negative q charge will come here, minus. This total will be minus q on the inner surface, but the total sphere was neutral, so it will have plus q outside. So plus q will come here on the outer surface. Total charge is 0. Here the flux is 0. Therefore, the field inside will remain 0. This is how it will be distributed. Okay. So here if we see that the in the metallic surface the field is 0. Inside the cavity field will be there. Now how about charge distribution? This outside charge distribution will be uniform because outside don't know how the charge is inside because there is no field line here. There is no field that is passing through inside the metal surface. There is no connectivity, I will say. Outside charge distribution will be uniform. Inside this, whether the charge distribution will be uniform or not, it will be uniform if the charge, this q is at the center of the cavity. If this charge q is not at the center of the cavity, that will be non-uniform. Okay, that will be non-uniform. So this will also be non-uniform. Outside will remain the uniform distribution. Getting it? So these are some details for concept clarity. Now potential due to induced charges. So let us discuss that condition I'm talking about. This is a sphere and I am bringing some charge q, keeping it here. What will happen? Say, sir, inside field has to be 0. So some redistribution will happen here. So some plus q charge, some plus charge, some positive charge. Oh, that I am considering positive, so negative will come on this side. So some negative charge will come here and some positive charge will come on the other side, like this. Now if I ask you, now these charges are what? These are induced charges. These charges are my induced charges. If I ask you, what is the potential at this particular point here? Okay, what is the potential at this particular point due to induced charges. By the way, let me tell you, this concept is not for mains. Okay, I'm telling you this concept for better conceptual understanding. This is not asked in mains. Now, what is this potential here due to induced charges? These are induced charges. Okay, now you may consider, sir, how to consider that, because how the distribution will be there, we don't know. Like how much charge will be at which location, we don't know. Even the distance is also is very difficult to find. So what we will do, we'll find the potential at center, total potential. This distance is, let us say x, the radius is r. Now whatever is the potential of the center, that is the potential of this point, because potential is same, electric field is 0. This potential V has to be the potential here has to be the, let us take Vc is the potential at center, and here the potential is V surface. So V center has to be equal to V surface. Now at center, if I write, due to induced charges, all the charges are at a distance r, total charge is 0. So due to induced charges at center is 0. Due to this charge q at center, it is kq by r, kq by x, the distance is x, is equals to, at surface, due to induced charges I have to find, let us take that as V, and at this point if I talk due to q, that will become k into q divided by this distance. How much is that distance? Root of, I'm taking this point here, okay, not tangent, this is here, this is 90 degree, okay. So this will become root of x square plus r square, x square, that is. So therefore I got this potential due to induced charges. This I am saying V induced. Kq by x minus kq by root of x square plus r square. This is not asked in mains. Earthing of a conductor. So let us take some conductor is there, any shape, maybe spherical or anything. If that is earthed, so what happens? The potential becomes 0. The potential of that surface will become 0, because this is a conductor, okay. So this is the surface of the conductor. The potential of conductor surface becomes 0, it means the potential of the conductor becomes 0. Grounding means the potential becomes 0. This point you have to consider. Not charge. Charge may become 0, may not become 0, depending upon other conditions. Other condition means presence of other charges also. Get it? If some charge is here, let us say plus q. So what will happen? Some negative charge will come from earth when you ground it, so that the potential of this will remain 0. Some negative will come. And if it is minus q, some positive will come. But the potential will become 0, not charge. Okay, now we are starting the next major topic, and that is capacitor. So basically, let us first talk about what is a capacitor. Okay, so two conducting bodies, whatever may be the shape, which are separated by a distance, and separated by a distance means in between the medium, that is insulator, or we say dielectric. Air is a dielectric, okay, non-conducting basically. So separated by some non-conducting medium, okay, and it behaves like a capacitor. Let us take these two plates here. These two plates are there. Okay, so one plate is connected with positive, another plate is connected with negative. So on one it will come plus q charge, another will come minus q charge. In between, what is there? In between, air is there, or vacuum is there, or some I'll say some another non-conducting material is there. Need not be this, has to be plates or any two random shape of conductors can be also there. Okay. Some charges will come like this. Okay, so this is potential. So we'll define the potential difference between these two conductors. That becomes my potential of the capacitor. Okay, potential of the capacitor means the potential difference between the two plates of the capacitor or two conductors of the capacitor. Let us take this is V1, this is my V2. So this is V1 minus V2, the difference of the two. This is V capacitor, that is across the capacitor, same thing. On one minus q charge will come, on another same opposite charge plus q will come. Okay, now basically capacitor is having some capacity of what? Capacity of storing charge. Okay, now we define capacitance, or sometimes we say capacity. Okay, capacitance of the capacitor, any two conductors plus q charge minus q charge, the capacitance C is equals to the charge of the capacitor. When we say charge of the capacitor, you may say, sir, charge is 0, total is 0. No, we don't talk about total, means how much charge is coming on one of them. So that is Q divided by the potential difference V. This is how the capacitance is, I can say it is the ratio of the charge divided by the potential difference between the two conductors. Now, does it depend on the charge and potential? Does capacitance depend on charge and potential? No, actually. Potential do not depend on charge and I'll say the potential. How? Let us take for a conductor. We say V is equals to IR. Some resistance is there, okay, of that conductor. Potential difference V is applied across this, current I is flowing. So we say V is equals to IR. V is equals to IR. So I'll say R is equals to V by I. Does resistance depend upon the applied voltage? No. Does resistance depend upon the current that is flowing through the resistance? No. But it is equal to the ratio of the two. Resistance depends upon the, you can say, resistivity and the dimensions, same. C is not dependent on Q and V. C depends upon you can say the dimensions, okay, of the conductor, the shape, the distance between them, all these things. Okay, it depends upon the shape, distance between, shape, distance between, or else is separation, not distance. Let us use separation. Shape, separation, and the medium between them. Okay, it depends on that. It is independent of Q and V, but it is equal to the ratio of, if I applied a potential difference V and the charge comes as plus Q and minus Q, so I'll say the capacitance will become Q divided by V. Okay. Now, unit of capacitance, that is farad. This is the SI unit. Okay, and we denote it with F. But this farad unit is actually very big. So generally you will find capacitors in questions of microfarad, millifarad, of nanofarad, all these values. Like farad is actually very big. Okay, although that is SI unit. Okay, but that is very big. So we generally have the expression, like units as microfarad, nanofarad, or not even millifarad. Actually, millifarad also you may find, but it's not generally there. Okay. Now dimensions. How to find dimensions? Many ways you may use the formula Q is equals to CV. C is equals to Q by V. Okay. Now what I can do? C is equals to Q by V I wrote, and from here I can say let us multiply with Q and Q. So this will become Q square divided by V into Q. V into Q is basically my energy. and Q square is there. Q I can write as current into time. Like this is how we have to like change two known quantities divided by energy. So if I write the dimensions of current, that is ampere, everything is perfect? Yeah, current, that is ampere. So this is ampere into time square divided by energy m L2 T minus 2. Okay, so what it will become from here? This is m L minus 2. T minus 2, when it will go in the numerator, it will become T to the power 4. T to the power 4, yeah, A2. I hope there is no mistake. Let us check it again. Q is equals to CV, C is equals to Q by V. I multiply, divide with Q. VQ becomes my energy. Q square I can write ampere into time. Energy ML2 T minus 2. So ML minus 2 ampere 2 and T 4. Perfect. Perfect. This is how we can write dimensions of capacitance. Yes, sometime it is asked. Dimensions of capacitance, dimension of epsilon naught, dimension of mu naught. Recently, they are frequently asked. Like most of the dimensions questions, if I see in the recent papers, so many times like mu naught, epsilon naught, C, electric field, magnetic field, energy density, these type of things are very frequently asked. So therefore, I was writing here. Okay, now types of capacitor basically. So few of the types of the capacitors that we will be discussing, almost I'll say 99% of the time we'll be talking about parallel plate capacitor. Okay, other than that we discuss is spherical capacitor and cylindrical capacitor. So in parallel plate capacitor, we have two parallel plates. They are placed at a distance, some distance. Let us take D here. Okay, connected to battery like this. In spherical capacitor, we are having two spherical conductors. Okay, and they are connected like this. There is some potential difference, that is inside and the outside conductor. Similarly, for cylindrical capacitor, we are having two cylindrical surfaces separated by some non-conducting medium, maybe air or anything. Okay, and inside and outside conductors are maintained across a potential difference. Now coming to parallel plate capacitor. Parallel plate capacitor. So most of the times we'll be discussing about parallel plate capacitor. So let us talk about. So here the two plates of the parallel plate capacitor, they are, I'll say, very close to each other. Although their size is very small, but because they are very close to each other, they'll behave like a infinite sheet. Okay, so they'll behave like infinite sheet because they are very close to each other. Therefore, I'm saying here the electric field will be uniform. Here the electric field will be uniform as we have in the case of infinite sheet. So electric field is uniform now. Let us take here the potential is V of the battery. So if I write, let us take electric field is E in this case. Now you have two sheets. This is one sheet. This is another sheet. This is having charge plus Q. This is having charge minus Q. Let us take here surface charge density is sigma, here minus sigma. If I talk about what is electric field in between, you'll say we'll take due to both the sheets, due to first sheet, it is towards the right, that is sigma by 2 epsilon naught, plus due to the second sheet, that is towards it, and that is also sigma by 2 epsilon naught. So here I got electric field as sigma by epsilon naught, sum of the two. Okay, so I got the electric field. What is sigma? Sigma is charge per unit area, that is Q by A. So here I can say that the potential, because we know that if the electric field is uniform, I'll say the potential difference will be E into D. I'm just talking about the difference, not the sign from which is positive. We know this is at higher potential, this is at lower. In this direction, the potential will be decreasing. So the potential difference V, this is E into the separation between the plates, that is D. Here I wrote this as Q by A, that was sigma, and epsilon naught was there. So like this. Now E I got, let us put it here. So V is equals to Q by A
epsilon naught into D. Now from here, if I write Q by V, what is that? A epsilon naught by D. And this is what I was saying, this is capacitance. Q by V is the capacitance. So I'll got this as the capacitance, and this is my C. This is very important. Make sure you learn this formula. The capacitance of a parallel plate capacitor is A epsilon naught by D, where A is area of the plates and D is the separation between the plates. Epsilon naught is the permittivity. Getting it? Okay. Now, let us come to some questions. Now here, one thing you should understand is, you should understand what is the formula for electric field, how I got the electric field. Charge was Q, I wrote electric field as sigma by epsilon naught, and the sigma I related with Q. Okay, so that also you should keep in mind. Now let us discuss this question. A simple pendulum of length L is placed between the plates of parallel plate capacitor having electric field E as shown in the figure. The bob has mass M, charge Q, the time period of pendulum is. Now what is the formula of time period of pendulum? If there is only gravity, you'll say that is 2 pi root L by G. We know that formula. Okay. Now if let us take additional other forces there. So what we will say, the electric field the time period formula will become 2 pi root L by G effective. That's all. Instead, in place of G, we will take G effective. Now here, what is G effective? G effective, if you see, one force mg is there, another force is there, that is due to the electric field. And what is that? That is electric field into Q. What is the additional acceleration? Okay, so this is my additional acceleration. Another one is acceleration due to gravity, another is this. Both are perpendicular to each other. Therefore, when I say G effective, that is root of G square plus EQ by M square. Why I am squaring this? Because both are perpendicular. To take the resultant of two perpendicular vectors, you can take root of one square plus another square. So I got G effective. Now I'll put this G effective here. By putting that here, which formula will match with our answer? That is A. So it will become 2 pi root L by G square plus EQ by M square. Now this question was a combination of capacitor and oscillations. So these type of questions, I'll say, are very interesting. Like two topics are asked here at the same time. Now energy stored in capacitor. Let us take a parallel plate capacitor. It is having some charge plus Q minus Q on the plates. If I ask you how much energy is stored in the capacitor, you will say how much work we did or how much work is done to make this positive charge and another negatively charged. That's only we need to do. So let us take at any instant, here the charge is plus Q and here the charge is minus Q. And I am transferring plus dq charge from here to here. Now what will be the work done in this? Because here electric force is towards the, I'll say this is positive because it will be pushing it. Electric force is towards the right. I will be applying the same amount of force towards the left because I'm transferring this charge very slowly. So if I ask you what will be the work done in transferring this separation is D. What is electric field here? Electric field, we know that is sigma by epsilon naught, and sigma is Q by A. So electric field we know, okay, and how much work, charge we know. So force will be E into dq. How much work we need to do? That will be E into, means whatever is the potential difference that will come into dq. So potential difference you can write E into D. So potential difference will come Q by A epsilon naught into D. This is potential difference into the charge dq, and this is my dw. Integrate it. So if I integrate it, what it will become? Q by A epsilon naught and integration, okay, D is constant, I'll take D out. Okay, so D is constant, I'll take D out. So this will become D by A epsilon naught integration of Q into dq, and this is my W. It is from 0 to, let us take the final charge as Q, okay, plus Q minus Q, capital Q I'm saying. So D by A epsilon naught, and this will become Q square. When putting the limits, it will become Q square by 2. This is W. And this work is stored as the potential energy. So this is my U. So what is U now? U becomes Q square by 2. And what is this? A epsilon naught by D? So C. So Q square by 2C. So this becomes the energy stored in the capacitor. Getting it? This becomes my energy stored in the capacitor. Now, I did for parallel plate capacitor. You can do other cylindrical or spherical capacitor also. It will come out to be the same. Now, can I write this in terms of other two variables, like including other two variables as well? Because I know that Q is equals to CV. This relation, if you use, you can replace Q by CV. So what it will become? It will become half CV square. Okay. If I replace C instead of that, so what it will become? So you replace C with, you can say Q by V. So it will become half QV. So any of the expression, like the formula we have for power, and that is dissipated in a resistor, that is I square R, we can write. And if you write that formula in terms of V and I, so it will become VI. And if you write that formula in terms of V and R, it will become V square by R. It's the same thing. You understand that? Yeah. So this is an important formula, you need to remember it. So how much energy is stored in a capacitor? That becomes Q square by 2C. And if potential is given, I'll use the formula half CV square. And let us take, if I know Q and V, I can use that also. Now, coming to a question, let us read it out. A capacitor with capacitance 5 microfarad is charged to 5 microcoulomb. Okay, if the plates are pulled apart to reduce the capacitance to 2 microfarad, how much work is done? Now, initial capacitance was 5 microfarad. What is final capacitance? 2 microfarad. Now, when you are pulling these plates apart, what is happening? Some energy would be changing in the capacitor, and that is equal to the work done. Let us find what is the energy that is changed. Okay, so if I write the initial energy, I'll say that is half what we know, charge. Charge is given to us. So it means charge remains the constant. Potential will not remain the constant. It is not connected with the battery. If it would be connected with the battery, then charge will not remain the constant, because charge can come and like go also. Okay, if you the separation is changing. Now it is not connected with the battery, so charge is given. If you are pulling the plates apart, the charge cannot change. So I'll use formula Q square by 2C. So it will become Q square by 2C initial, and similarly for U final, if I write, so this will become Q square by 2C final. And what is work done? Final minus initial. Okay, so work done is equals to U final minus U initial, and this comes out to be Q square by 2 into 1 by C final minus 1 by C initial. This expression you need to use here. Don't remember this, I just wrote it properly. Okay, so don't remember these kind of things. Now just substitute the variables. So what it will become? Q is 5 microcoulomb, and this is also in micro. So the units 1 of the micro will get cancelled, and this is 1 by 2 minus 1 by 5. What is 1 by 2 minus 1 by 5? 3 by 10. Okay, so that will become 3 by 10. So what it is? Q was 5, so 25. 1 10 to the power minus 6 will remain. Okay, another will get cancelled by 2 into, this is 3 by 10. So this will become 3 by 10. What it is now? So this 5 we can cancel here, or what I can say, 10 to the power minus 7 it will become. That in that way also I can write. Anyways, So this is 75 divided by 2, 75 divided by 2 into 10 to the power, or 7.5 divided by 2 into 10 to the power minus 6. Is it proper? This will become 3.75. Yes, 3.75 into 10 to the power minus 6. A. Okay, some simple calculation was there. Let us check it if I did any mistake. No. Okay, got it. Now, energy loss during charging. Now, if a capacitor is there, let us take initially it is uncharged. Now, you connect it with the battery. So, some charge will go from the battery across the capacitor and some energy will be stored in the capacitor. So, battery is doing some work, some energy, some part of that work is stored in the capacitor and some part of that work or energy, I'll say, that is dissipated. So, how much is that is dissipated? So, I can say that, let us draw it properly. Okay. This was our capacitor. This is the battery. It is connected now. Potential is V here. Capacitance I am saying is C. Some charge will come, plus Q, minus Q. So how much work the battery did? If charge Q is given gone, like I'll say, if charge is Q is transferred by the battery, so the work done by the battery is how much? That is the charge Q into the potential difference V. This is the work the battery is doing. How much energy is stored in the capacitor? So we know that is half C V square. Okay. Now this work, some part of this work is stored in the potential energy and some part is dissipated as heat. So I'll say that this work done by the battery is equal to my heat dissipated plus the potential energy that is stored in the capacitor. Now put the things. This is Q into V, or Q I can write as CV. Okay. So this is CV into V. This is heat. And what is U? U is half CV square. And if you see heat from here, if you write heat from here, I can say heat comes out to be CV square minus half CV square. So half CV square. This much energy is dissipated and this much is only stored because U was also there. Okay, so I'll say half of that is stored and half of that is dissipated. Now, force between plates of capacitors, these are, I'll say oppositely charged, some force will be there between them. How much? Let's write that. Okay. Now, let us take this is positively charged. This is negatively charged. So when I'm saying how much force this plate 1 is applying on plate 2, so what I'll do, I'll see how much is the field due to this plate 1, okay, here, because the electric field is uniform, we know that. Electric field is uniform here, and that is like this. Okay. So when I'm writing force on this plate, that will be in this direction. It will be pulling it. So how much is that force? I'll say that force will be electric field. This is due to this plate, okay, due to other plate. Into the charge. So how much is that electric field? That is sigma by 2 epsilon naught. Here I'll not say sigma by epsilon naught, only due to other. Into what is charge? Sigma into A. Or I can say that is Q, same thing. Again, you can write this sigma as Q into A. So Q square into A by 2 epsilon naught. This is the field This is the charge. So force will become field sigma by 2 epsilon naught into the charge. Okay, sigma is qa, so this becomes q square by 2 epsilon naught into a. Don't remember this. Okay, just understand this concept. Next is energy density. Now in a capacitor, how the energy is stored? Energy is stored in terms of the electric field. Okay, so this is parallel plate capacitor. Here we are having electric field lines like this. Okay, so the energy is stored in this region in terms of the electric field. So how much is that energy? That we say that is the energy of the capacitor. How much is the energy of the capacitor? We'll say that is half CV square. This is the energy of the capacitor, half CV square. Okay, so if I ask you what is energy density, you'll say energy density will be energy divided by volume. This becomes my energy density. What is the volume? The area is A, the width, or I'll say this separation is D, so this is A into D. And this I can write as half. What is C? A epsilon naught by D. What is V? Electric field into D divided by A into D. So this D got cancelled, this A got cancelled, and this D also got cancelled. So what it is now? Half epsilon naught E square. And this is the energy density due to electric field. Doesn't matter whether that electric field is due to capacitor or I'll say parallel plate capacitor or any other type of capacitor. If the electric field is present anywhere, the energy density due to that electric field is half epsilon naught E square. This you need to understand, okay? This formula is important, half epsilon naught E square. You should remember it, okay? Now spherical capacitor, here we are having inner sphere and outer sphere. Okay, some potential difference is applied like this. Inner one got charge, that is plus q. Outer one, let us take, is having some charge minus q. Now we need to find V and we need to find q. By taking the ratio, we can write how much is the capacitance. Okay, so let us do this. If I write electric field at a distance, here E, so what it will be? So due to outer shell, the electric field will be 0 because this point is inside. Due to inner shell, what will be the electric field? That will be K into Q, because this is outside this shell. This shell will behave like a point charge at the center. So that is KQ divided by R square. KQ divided by R square. How much is the potential difference? Just integrate. So KQ divided by R square dr. Okay, and R goes from A to B. So just I need magnitude of this. Okay, this becomes my V. So what it is now? So this will become KQ minus 1 by R, limit from A to B. So this will become KQ, and just taking the mode. Okay, so this will become B minus A divided by AB. Is it proper? Yeah. So this is V. Now Q by V, I'll take, if I write Q by V, what it is now? So this will become 4 pi epsilon naught AB. I am putting K as 4 pi epsilon naught divided by B minus A. So this becomes my capacitance. This is my C. The formula for capacitance for a spherical capacitor. Okay, formula for capacitance for a spherical capacitor. So inner radius is A, outer radius is B. This becomes the formula. Now sometimes what happens, there is only single sphere, then the capacitance is asked. When there is only one sphere, I'll consider the others, I'll say the outer sphere to be at infinity, then B will become infinity, and in that particular case the formula will remain just 4 pi epsilon naught A. B becomes infinity, so this will get cancelled, so this will become 4 pi epsilon naught A. So if there is only single sphere, the capacitance is 4 pi epsilon naught R. Okay, if there is, I'll say, I'll write here, if there is only one sphere, let us take, having radius R, I'll say for this the capacitance is 4 pi epsilon naught r. Considering other sphere at infinity. Okay, now there are sometimes variations also in this. So then you need to consider where the electric field is basically. Here the electric field is between this region, between the two radius. Okay, inner and outer. Therefore, we can use this formula. If the electric field is anywhere also, then you need to consider that also. But in mains, that's not required. Just remember this formula. Let us discuss this question asked in 2022. Capacitance of isolated conducting sphere of radius r1 becomes n times when it is enclosed by a concentric conducting sphere of radius r2 connected to earth. Okay. So the ratio of radii r2 by r1. So initially, let us take the radius was r1. If I ask you what is the capacitance, you will say 4 pi epsilon naught r1. Just okay. Now this is C initial C1. Now this is enclosed by R2. Now I'll ask you what is the capacitance. You'll say C2, that is 4 pi epsilon naught R1 R2 divided by R2 minus R1. Then the ratio of R2 by, now what is given to us? The capacitance becomes n times. Now C2 is n times of C1. This is given, this condition is given. So make that. So what is C2? C2 is this. So 4 pi epsilon naught R1 R2 divided by R2 minus R1, and this is equal to what? This is equal to this 4 pi epsilon naught R1. So 4 pi epsilon naught R1, this got cancelled. Oh, I missed n. N was here. Okay. So I can say this R2 is equals to n times R2 minus n times R1. And from here, I need to find what? I need to find R2 by R1. So R2 is equals to R2 by R1. I'm writing properly. Any mistake here? No, nothing else. No mistake. Okay, yeah. So R2, how I can write it? R2 by R1 by taking this on the other side. So this will become n minus 1 and here it will become n. So that is n upon n minus 1. So n minus 1 and this will become n. So this will become n upon n minus 1, that is option A. Yeah. Okay. It was simple, not complicated, but you need to understand what is the formula for spherical capacitor. Now here we are having cylindrical capacitor. The same exercise, what I'll do, I'll find what is the, because electric field is in between the two, inner and outer one. So what is the electric field at a distance r from here? So this is a charged, I'll say, hollow cylinder. So at a distance r, outside if you write the field, this will behave like a wire that is charged like this. So if I write electric field there, so that will be 2k lambda by r. Simple. This is my electric field. I need to find the potential. Okay, so just integrate it. 2k lambda by r dr. Okay, just I need the magnitude of this. Okay, so what is the potential difference from here? 2k lambda r will become ln r and limit will go from inner radius to outer radius. So what is inner? What is outer here? Let us consider A and R1 and R2. Okay, so R1 and R2. So this will become 2k lambda ln R2 by R1. Okay, so we got V. Now this V will write as Q. Okay, wait a minute. From here I need to write C. So first I need to replace this lambda in terms of Q. So I'm taking here a length L. Okay, length L. So if I write Q for this, so Q will be equal to lambda into L. So lambda I can write as Q by L. So putting it there, so lambda is Q by L. L I am using like this, ln R2 by R1, and this is my V. Okay, so easily we know that Q is equals to CV. So C is equals to Q by V. Okay, so Q by V, if I write, so this will become what it is. So it will become L divided by 2K ln R2 by R1. It is correct? Yes. Okay. Now this K I can write as 1 by 4 pi epsilon naught. So this will become 2 pi epsilon naught L by ln R2 by R1. This becomes my capacitance. And here generally we say capacitance per unit length. So if I write capacitance per unit length, okay, from here, capacitance per unit length, so what it will become? That will be 2 pi epsilon naught divided by ln R2 by R1. So any of that you can remember, either capacitance per unit length or capacitance. So this becomes the formula for cylindrical capacitor. Now coming to the next concept, that is redistribution of charges. Let us take two spheres are there having different charges, okay, maybe of different shapes also. Now if you connect them, initially they were not connected, if you connect them with a wire, let us take, so what will happen? The charge will transfer. How much charge will transfer? Until when the charge will transfer? Till the point they both have the same potential. So when the transfer of the charge will stop, I will say both will have the same potential. This is the concept. Two spheres initially might be having some potential V1, V2, some charge Q1, Q2. When you connect them, finally the charges might be different, Q1 dash, Q2 dash, but the potential will be same. Potential will be V1, V and V, I'll say. Both will be having same potential. This is the concept. Okay, we'll come to questions also. Same thing, like if two capacitors are there, let us take two capacitors are charged, and if you connect these two capacitors in parallel, so what will happen? Let us take initially they were having some charges. Now some transfer of the charge will happen from one capacitor to another capacitor, isn't it? So till when it will happen? Till both have the same potential. So both will have same potential. Some charges may come, their charges might be different, they might be same if the capacitors are same. Okay, so this is what we are going to do here. Let us read this question first. In the figure shown, after the switch S is turned from position A to B, the energy dissipated in the circuit in terms of capacitance C and total charge Q is. Now initially it was connected, it was having some charge Q, I transferred it from A to B. Now what is the energy dissipated in terms of Q? You understood this concept? If you understood, comment, you understood in the comment section. I need to know like whether you are getting this concept or not. Okay, so the transfer of the charges will happen till the moment the potential is same. Now initially it was connected like this. What is the charge initially? The charge initially is Q, that is CV. Okay, V here the battery is E, so I'll say that is C into E, like that. Now it is connected here. Now both the capacitors are in parallel. Both the capacitors are in parallel. What is the initial energy? Initial energy will say half C in terms of Q, let us write. So I'll say that is Q square by 2C. This is the initial energy. What is the final energy? So when the switch is shifted to B, some transfer of the charges will happen, but total charge will remain the same or not? Total charge will remain the same. So when I write the final energy here, Q will remain the same. Q square divided by 2 into here, the capacitance is the effective of the combination of the two. So these two capacitors are in parallel. C effective. These two capacitors are in parallel. How to find the capacitance of two capacitors in parallel, that we are going to discuss in combination of capacitors. So we will discuss that soon. But if the two capacitors are in parallel, the capacitance is C1 plus C2. You should remember that. So C1 plus C2. So C effective is C1 plus C2 is 3 plus 1, that is 4C. Okay. Now the energy dissipated is initial minus final. That is the energy dissipated. If you subtract that, what it will become? 3 by 8 Q square by C. Is it correct? This is 1 by 8, 1 by 2, yeah, 3 by 8 Q square by C. Another way, the longer way. Here this is the shorter way. The longer way is to individually find how much charge is coming. How you can find that? You can consider, let us take this charge was Q, some X amount of charge went to other capacitor. Equate the potentials. So this, its potential is Q minus X by C. That potential will be X by C, because we know Q is equals to CV, so V is equals to Q by C. Okay, equate them, that is 3C. Equate them. From there, you need to find what is X. So this will become 4X by 3. Okay, yeah. So from here, I got X is equals to 3Q by 4. From there, you can write how much is the charge now. Q minus 3Q by 4. This is Q by 4 and this is 3Q by 4. I got the final charges. I can find the final energies of the two capacitors. Add the final energy, I'll get what is U final, and if you add individually, you'll get the same thing actually. So I told you a shorter way here. Okay. Moving further, combination of capacitors, series and parallel. So if two capacitors are in series, let us take here we are having three capacitors. First capacitor having capacitance C1, second capacitor having capacitor C2, third capacitor having capacitor C3. This is a battery connected here. Now, some charges will come in series. The interesting thing is, when the capacitors are connected in series, the charge will be the same. Each capacitor will have the same charge. Why so? If Q charge is coming from here, this get plus Q, and here you'll see Q charge will come from other side also. This will get minus Q. And this total charge is 0. So this will be minus Q here, this is plus Q here, this is minus Q here, this is plus Q here. So all the capacitors in series will have the same charge. That we got? Perfect. Now let us take the individual potentials is V1, V2 and V3. If I write the total potential here V, you will say that is V1 plus V2 plus V3. Now Q is equals to CV, V is equals to Q by C. How much charge total went? That is Q by C effective, considering this to be an effective capacitor like this, one single capacitor. Okay, C effective, or I can say C equivalent, anything. This is, let us use equivalent word because that is mentioned here, C equivalent. Okay. And what is V1? V1 you will say again, that is Q by C1. What is V2? Q by C2. What is V3? Q by C3. Sometimes the students are confused. Sir, three capacitors are in series. First is having charge Q, second is having charge Q, third is having charge Q. So total 3Q charge came from the battery. No. From the battery here, Q charge is coming. Okay. Don't get confused. So from here I can say 1 by C equivalent, that is 1 by C1 plus 1 by C2 plus 1 by C3. And if there are other capacitor also, we can find like this. So this is how we find equivalent capacitance in series combination. Now for parallel combination, let us take these three capacitors are connected in parallel across a battery like this, and this is represented, this whole is represented with the help of a single capacitor having capacitance C equivalent. Each is having potential V because they are connected in parallel. Okay. Charge will be same or different? Charge will be different. Why same? Total charge from the battery that went is Q. Okay, so equivalent capacitance is having charge Q. So for equivalent capacitance, if I write that Q, that is C
equivalent into V. Okay. Now what is Q? Q I can say as sum of the charges, because this is the total charge that came from the positive terminal. So sum of the three charges, Q1 plus Q2 plus Q3. So Q1 plus Q2 plus Q3, this is equals to C equivalent into V. Now what is Q1? Across this the potential is V. So Q1 I'll say V into C1. Q2 V into C2. Q3 V into C3. So from here I got C equivalent as C1 plus C2 plus C3. And if there are other capacitors as well, we can add them like this. Now in resistors, we used to have such formula for series. It's just the opposite. Like in resistance series R1 plus R2 plus R3. But here when the capacitor is there, it's just the opposite. In parallel, we have C1 plus C2 plus C3. In series, we have 1 by C1 plus 1 by C2 plus 1 by C3 like that. That is 1 by C equivalent. Now let us discuss a question on the combination. Let us take here, this capacitor is having 4 microfarad capacitance. Then we are having a capacitor of capacitance 2 microfarad. And let us take this as 5 microfarad. And I ask you, how much is the C equivalent? Okay, simple question first. So these two are in series. First, these two are in series. Find the equivalent of these two. So 1 by C equivalent is 1 by C1 plus 1 by C2. That will become C1 C2 divided by C1 plus C2. So that is 8 by 6. C1 C2 divided by C1 plus C2. So that is 4 by 3. So this is 4 by 3 and this 5 are in parallel. So C equivalent will become 4 by 3 plus 5. Getting it? Now let us consider there is a battery. Connected here, and it is let us take simple value 10 volt. If I ask you what is the charge across 5 microfarad, you'll say charge across 5 microfarad, potential is 10 volts, so Q is equals to C into V. So here the charge for 5 microfarad, that will become C, what is 5 into 10, 50 microcoulomb. If I ask you what is the charge across 2 microfarad, how will you find that? Now these two are in series, both will have same charge. Because they are in series, they'll have the same charge. What is the equivalent of this? Equivalent is 4 by 3. So this equivalent capacitance represent these two. Okay, so 4 by 3, one capacitor is there. The battery is 10 volts. So I'll say Q, that is C into V. C is 4 by 3 into V, that is 10. This much microcoulomb. What is this? 40 by 3 microcoulomb. And that is same across those two. So I'll say this is my Q 4 microfarad capacitor and 3 microfarad capacitor. Okay, same charge is coming across both of them. How much total charge went from the battery? You'll say that is 50 micro for this and 40 by 3 for this. Getting it? That's all. So these type of questions can ask, like there can be multiple capacitors and he may ask you what is the charge across this capacitor. So then you need to understand how it is connected, the series parallel combinations. Okay, those things you need to consider there. Now Kirchhoff law. Okay, so we have Kirchhoff law in current and electricity also. So here also we will see how we can apply that when there is a combination of capacitors. So let us take there is a combination of capacitor. Which we already did. Okay, here charge is Q1, charge is Q2, charge is Q3. This is potential V1,
V2, V3. Move in a closed loop, the total potential, the algebraic sum of total potential gain or loss that will come out to be 0. Okay, so this is plus minus plus minus plus minus. So here I am going, initially there is plus V is equals to, for this capacitor going from positive to negative, there is a drop. How much drop? Not equal to, how much is drop? That drop is Q1 by V1. Sorry, that drop is of V1. So I'll say that is minus V1. So here I need to mention in terms of, let us mention in terms of capacitance. So I'm saying, let us take here capacitance is C1, this is C2, this is C3. Okay. So V is equal to Q by C. So drop first. How much is the drop? Q1 by C1. Then how much is the drop? Q2 by C2. Because this is a drop, therefore I am saying considering negative, minus Q3 by C3, and this is 0. This is my loop rule. Any loop. There may be like multiple capacitors, other capacitors as well here. Okay, so still you can apply like it. What we can consider here? You can apply, still this will be applicable because we are moving in this loop. Okay, so we can write this for this loop. This is my loop rule. Another is the junction rule. Okay, so another is junction rule. So what is the junction rule? The junction rule is any junction. Let's take this junction. These three plates are connected. 1, 2, 3. So the total charge, because this is not connected with the circuit, the total charge has to be 0. Let us take here the charge was Q4 plus minus. So when I say total charge, so this is minus Q1. Here this charge is plus Q2. You need to see the polarity as well. Okay. Here this charge is plus Q4. This is 0. This is my junction rule. Okay, so these two are the Kirchhoff rules. Now nodal analysis to solve problems. Let us take an example. Now these other details which I am mentioning, they may not be so much helpful for mains as it is. Okay, you may not get very complicated question where you need to use nodal analysis or like that, but I'm telling those things in a simplified manner so that you understand that concept, and even we can apply that as well. Okay, so nodal analysis, let us take, there are capacitors like I'm using a simplified circuit, by the way. Let us a simplified circuit I am showing you. Okay, that's all. Now here, this is voltage V. Now if we need to find charges across these capacitors, now one way is like series parallel combination we can see, and accordingly we can find like these two are in parallel, I'll get the equivalent. These two are in series, got the equivalent. I got the C equivalent, total charge I know now. So that much charge is coming across this capacitor. Now that charge will be divided across these two capacitors. I'll find the potential, the remaining potential there. And there I can say what is the Q1 and Q2 for these two capacitors. That we know, easily we can do. Now in nodal analysis, if I have to solve, so what I'll do is ground one of the point, and let us consider here the potential is V. Now what I'll do, so because I know the total charge of this system has to be 0. So this you may consider plus minus Q1, this you may consider as plus minus Q2,
plus minus Q3. So I'll say that is minus Q1 plus Q2, okay, plus Q3. This is equal to 0. Now how will I write V? So how will I write Q1 basically? So Q1 will be equals to this potential I am considering as V. This potential is V, this is 0, this is, okay, I considered here, let us consider this potential as X, not V, because V I already considered X. Okay, now let us write these charges in terms of X. Across, if I ask you what is the charge across Q2, so you will say that is X by this capacitance C2, this is C3, this is C1. So Q2 will be X, the potential across this is X by C2. Similarly, this is X by C3. What is Q1? This potential is V, this potential is X, across this the potential is V minus X, like this. So Q, okay, I'm writing Q, so this is CV. C into V, I did a mistake. V is X and C is C2, so this is XC2 and this is XC3. And similarly here Q1 I got, that is V minus X, minus of that, okay, so minus of V minus X C1, and this whole is equals to 0. This is how we can find the potential X there. This is nodal analysis method. If you didn't get anything, no need to worry, this is not required for mains. This is for conceptual clarity I am telling. Wheatstone Bridge. Now sometimes a circuit is given in which C1 by C3 is equals to C2 by C4. So if this thing happen, C1 by C3 is equal to C2 by C4. So this becomes a balanced Wheatstone bridge that we will study in great detail in the current and electricity chapter. In that what happens, these 2 points have the same potential. Same potential means charge across C5 is 0. Potential is same of the two ends of the capacitor, charge will be 0. If charge is 0, that capacitor becomes a dummy capacitor, you can remove it. So remove this. If you need to find C equivalent, now these two in series, find the parallel combination of these two series. This is how we can solve and get the value of charges or C equivalent or any other thing. Okay, provided this condition is followed. Only you can remove this when this condition is followed, not otherwise. Next is infinite ladder problem. Sometimes capacitors are connected in like in an infinite ladder like this, and there these are C and C, there may be different also, this one can be 2C also, like that they may be connected, and then you need to find the C equivalent. So how we need to solve that, these type of things. Now this is circuit, this is my given circuit. Now if I break this from this, I will be remaining with this part only. This is same as the original circuit only, okay, because this is infinite, this is same as the original circuit. So if I say the capacitance of this is X, so the capacitance of this part, and now this is also X, so this X in parallel, this X in parallel, so this C equivalent is also X, because it's the same thing, isn't it? So now you can say this is C plus X, okay, this capacitor says C plus X, that is in series with C, so C into C plus X divided by C plus X plus C, and this is equals to my X. From here you can solve for X, okay, so easy, like you take one portion, okay, and this is how it is repeating, this is also X, so and the equivalent of this is also X, so this plus X, this with this X is giving me equivalent X only. This is how you can solve X from this particular equation. Now symmetric circuits, so sometimes in circuits you will see some type of symmetricity, like in this circuit if I talk about in this upper portion there is a symmetricity, and what is that symmetricity, about which line you can see the symmetricity, that is about this line, okay, I am considering here the battery is connected like this. The symmetricity is about this line. This capacitor is coming on the symmetricity line. You can remove this because on line of symmetry the potential is same. You can remove this and then you can solve. Or what you can do is you can find the capacitance of half, like first initially I am doing by the simple logic. These two are in series C by 2, these two are in series C by 2, C by 2 plus C by 2, that gives me C equivalent. Okay. Or what I am saying, you just connect these 2 points, find the capacitance of this half, half will C and C parallel, it will give you 2C. Now this 2C and this 2C is in series now, isn't it? The same thing, like, so this will become C. The same way you can do. Next is multiple plates. There are sometimes questions on which multiple plates are given and then you need to find the C equivalent, like in JEE Advanced 2024. This particular question was asked there, matrix match was there and similar type of structures of parallel plates was there. We need to find C equivalent. So how to how we can solve these type of questions is, let us take the battery is connected like this. So some charges will come on the plates. So between these 2 plates, let us take the capacitance as C1. Between these 2 plates, let us take the capacitance as C2. Between these 2 plates, the capacitance is C3. Okay. Here the potential, let us take this is point A and this is my point B. So when you draw the equivalent circuit of this, you first show the 2 points. This is A, this is B. Is there any other point having different potential than A and B? There is no such plate in this. If there is such plate, then you need to consider a point C also for that. I'll show you. Now this C1 is connected between A and B because this is having potential of B, this is having potential of A. C1 is connected between A and B. This C2, one plate is with A, another plate with B, so C2 is connected between A and B. C3, one plate is connected with A, another with B. C3 is connected between A and B. C1, C2, C3, okay, they are in parallel. C equivalent is equals to C1 plus C2 plus C3. In the question, you will be given the separation. Okay, you will be given the area. So A epsilon naught by D, you can replace C1, C2, C3, and if the separations are same, the areas are same, so each C will be equal. So you can just say 3C if they are equal. So 3 into A epsilon naught by D. Like this. Easily you can write. We are having a question on this. Let us do this. 4 identical rectangular plates with length this, breadth this are arranged as shown in the figure. The equivalent capacitance between A and C is. Equivalent capacitance between A and C. Now here, C. We need to find between A and C plate. So you are connecting battery between A and C. That's the meaning. Okay. Now one thing, we have potential of A. One point is there, another point is C. We have these 2 points. Is there any other potential in this? Yes. B and C are not connected with A and C. So let us consider they are connected with each other. Potential will be same. So let us take the potential of these 2 plates is some, you may consider one point, another point. Let us take this point is my C. Okay. So when you write the equivalent capacitance, here I am considering the capacitance to be C1, this is C2, this is C3. Now when I draw the equivalent, how will I show? One point, this is my first terminal of the battery. I am considering this as A and this as B. Oh, you may be confused with ABCD. Let us make it 1, 2, 3. Let us make it 1, 2, 3. So I am considering this as 1. I am considering this as terminal 2. And we need one more additional potential. So this I am considering as 3. Now let us draw the equivalent. C1 is connected between one plate is at potential 1, another plate is at potential 3. So C1 is connected between 1 and 3. I am saying this is my 1, this is my 2 and this is my 3. So C1 is connected between 1 and 3. Simple. C2 is connected between 3, this is at 3, this is at 2. C2 is connected between 3 and 2. 3 and 2. C2. C3 is connected between 2 and 3. So between 2 and 3. Perfect. Between 2 and 3. Yeah. So I got this equivalent. Now these two are in parallel, C1 plus C2. And here the separations are same. Okay, so you can write this as 2C and this as C. So 2C and C are in series. So equivalent will be 2C into C divided by 2C plus C. So this will become 2C by 3. So what is 2C by 3? So this will become 2 by 3 A epsilon naught by D. The answer is in terms of epsilon naught by D. I need to put A. What is A? Length 2 into the breadth, that is 3 by 2, that will become 3. So area is 3. So this is 2 epsilon naught by D. So I'll say X comes out to be 2. This is the easiest way to do this type of questions. There may be other lengthy way, they are there, but this is the easiest way to do such type of questions. See how many different potentials are there, label that. 1, 2, 3. I got, show those points, connect the capacitors, get the equivalent. Another question. In the circuit shown, find C if the effective capacitance of the whole circuit is to be 0.5 microfarad. Okay. All the values of the circuit are in microfarad. So effective capacitance is given as 0.5. We need to find C. So let us solve it. Now first of all, I can see that these two are in series. So equivalent will be 1. This one and this one are in parallel. So the equivalent will be 2. The equivalent of this will be 2. This 2 and this 2 in series, so the equivalent of this whole will become 1. This 2 and this 2 in parallel, equivalent is 4 here. This 2 and this 4 are in series, so the equivalent will be 8 by 6 because 4 into 2 divided by 4 plus 2. So 4 by 3. Now draw the equivalent. Now draw the equivalent. This is C and this 1 and this I'll say this 1 and this 4 by 3. They are in parallel. This is 1, this is 4 by 3, this is C. So 1 and 4 by 3 in parallel. So what is the equivalent of these two? 1 plus 4 by 3, that is 7 by 3. So this is C, this as 7 by 3. These are in series. How to write the equivalent? You can write like 7 by 3C divided by 7 by 3C plus what? Sorry, I did a mistake here. 7 by 3 plus C. Yeah. C1 C2 divided by C1 plus C2, and this is given as 0.5. From there you need to find C. Are you getting this? If yes, solve this equation, put your answer in comment section. Okay, I'm not solving it further. I hope you are able to understand the concepts. So put your answer in the comment section. I'll see how many of you are solving these questions with me. Okay, moving ahead. In the given circuit, C1, C2, C3, C4, C5, C6 is given. The charge stored on the capacitor C4. So we have to find charge stored on C4. Now this question was asked in April attempt of 2023. Let us put the values first. C1 is 2 microfarad. C2 is 0.2. C3 is 2. I'm just writing the value now because each is having microfarad unit only. C4 is 4. C5 is 2. C6 is 2. Okay. Charge on C4 I need to find. Now, how we can simplify this? One way I'll say is this and this is in series, so it will become 1. This 1 and 4 is in series because these all three are in series. So 1 and 4 are in series, so equivalent will become 4 by 5. So equivalent of these three in series, or you can write 1 by C1 plus 1 by C2 plus 1 by like 1 by C3 plus 1 by C4 plus 1 by C5. So that way also you can find 1 by C equivalent, and this will come out to be 4 by 5, which is 0.8. That 0.8 and 0.2 are in parallel. So this whole is actually 1 microfarad. This is 1 microfarad. Now this 2 and this 2 are in series, that is 1. So 1 and 1 are in series, 1 by 2. Getting it? This 2 and 2 are in series, so it will give you 1 microfarad. Now that equivalent of these two 1 and this 1 are in series, so that will give you equivalent of 1 by 2. So from here, total equivalent of capacitance is 1 by 2. So if I write the charge, total charge, that is C equivalent into V, so that is 5 microcoulomb. 5 microcoulomb is going, so it will have 5 microcoulomb C1. This C6 will have 5 microcoulomb and this whole will have 5 microcoulomb. Okay, now what I can do is, how much is the potential across this? If I ask you how much is the potential across this, so you'll say V is equals to Q by C. Q 5 microcoulomb, sorry. Q by C, 5 by 2, 2.5. This is 2.5. This is 2.5 volt. 2.5 volt, 2.5 volt. Rest is, remaining is 5 volt. The rest remaining 5 volt is coming across this part. Now it becomes simple to me. This is having 5 volt and these three are having 5 volt. These three are having 5 volt. So across this, the potential is 5 volt. What is the equivalent of these three? Equivalent is 0.8. Each will have the same charge, so I will just say C equivalent into V. So Q will be C equivalent here into V. So 5 into 0.8, 4 microcoulomb. The charge is there, okay? 4 microcoulomb. I'm showing you how to analyze. I'm not writing anything here. I'm just showing you how to analyze. Let us repeat the exercise. Okay, just the method itself. First, I got the equivalent of this is 0.8 is parallel with 0.2. This become 1. This 1, this 2 are 3 in series. Found the equivalent, that become 1 by 2. 1 by 2 total charge will become 5 microcoulomb. So this will have 5, this will have 5 and this whole will have 5. Okay, so 5 microcoulomb means 2.5 volt here, 2.5 volt here. Remaining is 5 volt. So this will have 5 volt. C2 will have 5 volt. These three in series will have total 5 volt. These three in series is having equivalent 0.8. So the charge will become 0.8 into 5 in each of the three, because they are in series, they'll have the same charge. Therefore, I am saying just C equivalent into the potential, that is 5. Dielectrics and its types. Now, capacitors, many times, like generally when we say the capacitor is there, so two conductors are there and in between the non-conducting medium is there. Non-conducting means dielectric. Okay, non-conducting means dielectric. It can be air, it can be some other you can say material that is non-conducting, any of the material, paper, wood or something, anything. Okay, so dielectric is basically a non-conducting material, simple. This is a non-conducting material. So how many types of dielectric can be? Two types, polar and non-polar. polar means they have some dipole moment, like some solution is there. Okay, let us take water is there, so hydrogen and oxygen, so one is electronegative, another is electropositive, some dipole moments are there. Okay, so and non-polar means both are having same electronegativity positivity, so the dipole moment is 0. So in polar solution, if I say, now you may say, sir, what is this, we are not getting anything. I'm explaining now, you'll understand. So polar solution, when I'll say, the positive and negative charge centers will be there. In absence of electric field, I am drawing it, they will be randomly aligned. In absence of electric field, randomly aligned. And non-polar, plus and minus are overlapping. Plus and minus are overlapping. So here also the total electric field due to this is 0. Here also the total electric field is 0. External electric field in this case was 0. Here also it was 0. Now I am applying electric field. What will happen? These dipoles will be aligned. The positive charge will try to move in the direction of electric field. Okay, negative charge will try to move opposite. So they will be aligned like that. Okay, similarly here also the positive charge center and negative charge center will have force in the opposite directions. So here the separation will increase between positive charge and negative charge center, and effectively I'll say in presence of electric field, both will look like I'm just showing in little space here. Let us take electric field is applied towards the right. Both will look like this. Okay, now here external electric field was 0, I applied electric field, both will look like this. Both will behave like this. Here the separation will increase. Okay, here the alignment will happen. This is the difference. Both will look like this. Now what will happen? They will have their own electric field. Okay, they'll have their own electric field. Effectively, I'll say on this side negative charge is there, effective on this other side positive charge is there, so they will have their own electric field in the opposite direction like this, and I'll say this is the induced electric field. Okay, the due to the induced charges that came on the my dielectric slab. Getting it? So there will be some opposite electric field here, E induced, and the total electric field, if you talk about inside this, is my applied electric field minus the induced electric field. You remember that when I was saying if you change the dielectric medium, the electric field will become 1 by k if the dielectric constant is k. You remember that in the previous chapter we discussed. So this is what exactly happens. Okay, so there is some induced electric field. Okay, that is in the opposite direction, so it makes the actual electric field lesser. Okay, therefore we will say that the electric field will become effectively 1 by k times of that. Okay, now effect of dielectric on capacitance. This is a parallel plate capacitor. Initially you can say the free space is there in between, so we write the capacitance as A epsilon naught by D. Now what I did, I inserted a dielectric slab. I inserted a dielectric slab in between like this. Now if I ask you what is the capacitance now, you will say if the dielectric slab is there, epsilon will change. Here we have to take the permittivity of this medium now. Okay, so this is how my capacitance will change. I'm not going to very great detail. I'm just talking the things that are relevant to JEE mains, relevant for JEE mains. Now dielectric constant. So we define the dielectric constant for a dielectric by K Okay, we say that is my dielectric constant. So the permittivity is epsilon into epsilon naught into the dielectric constant. So when I was saying C dash was A epsilon by D. Okay, so that will become A K epsilon naught by D. So this capacitance is getting K times. This capacitance is getting K times. Try to understand. If a capacitance is there and the medium between the plates is filled by dielectric constant K, then the capacitance will become K times of C. If it is completely filled, I am talking about. If it is half filled, we will talk about that. So if dielectric is having constant K, capacitance will become K times of C. Capacitance when dielectric is partially filled. Okay, let us take the capacitance. The capacitance initially was C, and now it is partially filled, and we need to find what the capacitance will become. Let us take like this. It is filled. It is having dielectric constant K. So it will behave like two capacitors. Let us take this was D, this is T. It will behave like two capacitors in series. This is having T, so this separation is T, this separation is D minus T, the remaining one. Here the dielectric is there having dielectric constant K, and here air is there, and from here I will find the C equivalent. Okay, and let us take the dielectric is filled other way. Other way means let us take it is filled like this. Half I am considering. Let us take half. Dielectric constant is K. Now it will behave like two capacitors in parallel. Okay, upper one and lower one. Here the dielectric is there K. Here the air is there, and from here I'll say C equivalent will get. Okay, so this is how you can like simplify to find the equivalent capacitance. Let us do this question. A parallel plate capacitor has plate area 40 and plate separation 2 mm. The space between the plates is filled with a dielectric medium of thickness 1. Dielectric constant and dielectric constant 5. The new capacitance of the system is. Very easy question. Now initial capacitance was what was the initial capacitance? Okay, that is not mentioned, we need to write that. Let us take this was the capacitor. Now the dielectric field, total thickness, total separation was 2 mm. In 1 mm, here dielectric is filled, and the dielectric constant for this is 5. This will behave like a two capacitors in series. Its separation will be 1 mm. This separation also 1 mm. Here the dielectric is 5. Let us take this is C1, this is C2. If I write C1, what is that? Area A epsilon naught K, because K is there, so K epsilon naught by D. D is 1 mm. And C2 if I write, that is A epsilon naught by D is again 1 mm. Okay, now these two are in series, and area is also given as 40 centimeter square. So let us put A as 40 centimeter square. So 40 into here it is 5, and the centimeter square, so 10 to the power minus 4 is there, here 10 to the power minus 3 is there, so minus 1, so by 10. epsilon naught. Okay, and here if I say this is 40 by, again factor of 10 will come. Yeah, yes. So C1 is basically 20 epsilon naught and C2 is 4 epsilon naught. Now if I want to write the equivalent, so this is C1 C2 divided by C1 plus C2, 20 into 4 divided by 24 epsilon naught, 4 into 6, 10 by 3, 10 by 3 epsilon naught farad. Got it? Simple, easy question. Yeah, another question here, it is in parallel. Okay, so again we will say that it will behave like two capacitors, okay, connected in parallel, and the capacitor of 10 microfarad. Okay, let us read it now. Capacitor of capacitance 10 microfarad whose plates are separated by D through air, and each plate having area A is now filled equally. Initially the capacitance was 10 microfarad and this was my A epsilon naught by D. Now the dielectrics are filled like this. Okay, so the area is half, symmetrically they are filled. Okay, so here area is A by 2, here area is A by 2, the separation remains the same. So if I say for this capacitor and this capacitor, okay, if I say C for this, so A epsilon naught, A is A by 2, epsilon naught is 2, epsilon is 2 epsilon naught, K epsilon naught by D. Okay, similarly here this is A by 2, K is 3 epsilon naught by D. Okay, now A epsilon naught by D and 3 by 2 A epsilon naught by D, these are in parallel, so add that, so total will be 3 by 2 will plus 1, 5 by 2 A epsilon naught by D. Now what was A epsilon naught by D? That was 10 microfarad. So from here I got C equivalent or C effective here, that will be 5 by 2 into 10, 25 microfarad. Getting it? 25 microfarad. Now this is, I'll say, sometimes a confusing question, how we need to consider sometimes whether we need to consider K1 K3 in parallel, then K2 K4 in parallel, okay, or we need to consider K1 K2 in series parallel with K3 K4 in series. So here I'll say that potential of this point and this point is not equal. So don't say the potential across K3, K1 and K3 is same. No, the potential across K2 K4 is not same. Okay, so first I'll say K1 K2 they are in series, K3 K4 they are in series, find the equivalent, then they are in parallel. So it will become like, if I say this is C1, C2, C3, C4, so you write it like this, C1 that is in series with C2, here C3 that is in series with C4, and from here you find C equivalent, okay, by writing the same way. So if we solve from here, we will get the answer as B. Okay, so you can solve it, you can try to simplify the final equation, you'll get option B as the correct answer. Now capacitance when metallic slab is partially filled. Now when metallic slab is filled, in metallic slab there is no electric field in that region. Okay, so if I say, let say this is my capacitor. Okay, so here if I fill a dielectric a metallic slab like this, I need to select a different color. Let us take, this is my metallic slab. So what here the electric field will be 0 at electrostatic condition. This thickness is T. So in this region the electric field is not there. So it will just behave like one capacitor having thickness D minus T. Okay. Here the electric field is not there. Moving ahead, variation of different variables. Now we are having a parallel plate capacitor. Now dielectric is inserted. How the electric field, how the other variables will change, let us talk about. So initially air is there, plates are connected with a battery. Now let us write the initial variables. If I talk about the electric field, what is electric field? Electric field, you will say, sir, that is my sigma by epsilon naught, Q by A epsilon naught. Potential is V. What is Q? If you write Q, that is CV. C is A epsilon naught by D into V. What is C? C is A epsilon naught by D. Okay, let us write these three variables, these four variables. Now, we inserted dielectric, battery is connected. Now, battery is connected, charge will change or not? Charge will change. Capacitance, if I write capacitance, that because dielectric is K, so capacitance will become K times of A epsilon naught by D. Okay, so I'll say this is K times of C. If I talk about here potential V, we will remain the same, battery is the same, we will remain the same. Yes, we will remain the same. If I talk about electric field is V by D. You may say, sir, but if dielectric is K, initial was E, electric field should change, isn't it? No, here charge will change, electric field will remain the same. And if I talk about charge, Q, I'm writing these as dash. V dash is V only, E dash is E only, and Q dash, that is C into V, C dash into V. C dash is K times of that. So this will become K times of CV. So this is K times of my original charge Q. Getting it? So charge will change. Second case, if the battery is not connected, charge cannot change, charge will remain the same. Charge will remain the same. So if I say in this case, capacitance C dash will be certainly K times of C, Q dash will remain Q. If I talk about electric field, this will change. Electric field will change. That was sigma by epsilon naught Q dash by A epsilon naught. Okay, Q dash is sorry, I did a mistake here. So here when I say sigma dash, sigma is same, Q is same. So sigma divided by this is my E dash divided by epsilon naught. Here this is epsilon, so medium is there. So epsilon, that is K times of epsilon naught. Okay, so this is Q by K epsilon naught A, or I'll say this is my E by K. If I write V dash, V is E dash into D. If E is getting 1 by K, V will also get 1 by K. Okay, this is how the variables changes. You need to understand this difference. Many times the question is asked, what if the batteries remain connected? What if the battery is removed? So all these things are asked. Now dielectric breakdown. When we talk about dielectric medium, we say non-conducting, it is non-conducting. But what if you apply very high electric field? What happens? Very high electric field. What happens? It will become conducting. Yes, in the case of lightning also from the clouds. So when the charges in the clouds are very high, I'll say like in magnitude. Okay, so what happens? Very high electric field is there. So when very high electric field is there, even air becomes conducting. Air becomes conducting and there is a lightning strike like that. Okay, so I'll say that what happens there is a dielectric breakdown. So dielectric breakdown happens when the electric field is greater than the breakdown electric field. Okay, so electric field is very high. In simple word, if I say if E is very high, dielectrics become, or I'll say dielectric become conducting, okay? Conducting, and this we say as the dielectric breakdown. Okay, this we say as dielectric breakdown. Why this happens? Now, the electric field is very high. Although the electrons were not present in the conducting band, what happens? The valence band electrons are, I can say, pulled by the very high electric field, and due to which they start conducting. Okay, in simple words, I am telling you this phenomena. Now, let us do some questions further. A parallel plate capacitor with plate separation 5 mm is charged by a battery. It is found that introducing a dielectric sheet of thickness 2 mm while keeping the battery connections intact, the capacitor draws 25% more charge from the battery than before. The dielectric constant is, what is the dielectric constant? Okay. So, battery is connected. When you insert dielectric, what happens? It draws 25% more charge. So, Q dash is 25% more than the initial charge. Battery is connected, V is same. Q dash is C dash into V. V is same. So, C dash becomes 1.25 times of C. Okay. Now, how the dielectric is inserted? The separation was 5 mm and in 2 mm we are having dielectric. And what is the dielectric constant? Okay, we need to find. Let us take this as K. This remaining is 3 mm. So these behave like C1, C2 in series. What is C1? A epsilon naught, K epsilon naught by D. D is 2 mm. Okay. Yeah. And what is C2? C2 is A into epsilon naught by D. D is 3 mm. Now these C2, C1, C2 are in series. Okay. So if I write equivalent from there, C1, C2 divided by C1 plus C2. A epsilon naught I am taking common. Yeah, C1, C2 divided by C1 plus C2. So K by 2 into 1 by 3 divided by K by 2 plus 1 by 3. Okay, and that mm term will also be there because I have considered that in mm. Anyways, initial capacitance, initial capacitance, if I write initial capacitance, my C, what is that? A epsilon naught by 5. I am writing in mm only. A epsilon naught by 5. So I can say that A epsilon naught is 5 times of C. This is 5C. So I'll say this is 5C. Okay, 5C, and this is K by 6, and this is 3K, 3K plus 2. So by 6 anyway will get cancelled. So this is 3K plus 2. Everything fine? Hope so. Yeah. Okay. 3K plus 2, and this C equivalent is 1.25 times of C, that is 5 by 4 times of C. So this 5C is getting cancelled, and we got 4K is equals to 3K plus 2, and we got from here K is 2. Some calculations were there in this question, although the concept was not very difficult, but some calculation is there. In such questions, yes, we can say sometime it will take at least 2 minutes when you are very fast. Another question, a parallel plate capacitor of capacity C and 3C are connected in parallel combination and charged to potential difference 18 volt. The battery is disconnected and the space between the plates of the capacitor of capacity C is completely filled with material of dielectric 9. the final potential difference across the combination will be. Okay, so initially both were connected across a battery having 18 volt capacitance, 18 volt potential, C, 3C, this is V, this is 18. Now they will be charged. How much charge will come? Here CV, on this the charge will be 3 CV. Now space of capacitance having capacitance C is filled with a material of dielectric constant 9. So this space is having dielectric constant 9. So here for this, if I say my C dash is 9C. The final potential across the combination, now these are connected in parallel. So some redistribution will happen because dielectric has inserted capacitance changes, so redistribution of the charge will happen. So when I have to write the final potential V dash or V final, how will I write? Q is equals to CV. V is equals to the total charge divided by the total or the effective capacitance. What is the total charge? Charge will remain the same. Whatever was the initial charge, because battery is not connected, that total charge will be same. How much is that? CV and 3 CV, that is 4 CV divided by. These two capacitors are in parallel, 9C and 3C. What is the equivalent? 9 plus 3, 12C. So this is V by 3, V is 18, 6 volt. If you do by this method, it will save time. If you go try to find the individual charges and then solve, it will take a lot of time. So use this simplified method, that will help you. So this is all from my side. I hope you understood all the concepts, and if you are till this point of the video, make sure you comment completed so that we can see that how many of you are watching it completely. At the same time, go in the description box, click on the link, you'll go to our app. From there you'll get DPP, okay, for this, because these practicing questions is very important. You are seeing me, I'm solving it. Few things you may say, oh, I got this question, but when you will solve, you may not be able to do that. Therefore practicing is very, very important. So make sure you practice the question from the DPP given in the link in the description below. Thank you all.